Um, it's okay. Is it really straining your eyes to look at the gray? I'll post it on YouTube afterwards. Actually, maybe first. Okay, sorry. Need to get situated really quick. Yeah, so I'm sorry for being slow. Depends on the colors. You can let me know if the gray is annoying. We can switch to white. Okay, so here's the deal. In case you haven't been to a review session of mine before, I've got a bunch of examples prepared, which are all, in my opinion, relevant. Also, if everyone wants to mute, I don't know if that was, at least right now, I don't know if that was on already. Anyway, so I have a bunch of examples prepared. If you throughout the night, we can also do other things, like we can talk about the practice midterm. We can talk about any questions that you have. We'll see how things go. Also, I said 6 to 9, but I'll go until I get tired. So if that means 10 or 11 or whatever, we'll see. Maybe not that late, but at earliest, I'll stop at 9, and I'll sit here and do math until I get bored. Probably not an all-nighter, just because the exam comes out in less than 6 hours. So earliest 9, latest 12. And with that, is the multiple choice like the ones that we have on the mock midterm? Yeah, it's pretty similar. Overall, the practice midterms are pretty indicative of the real thing. So if you need to do one thing, it's probably work through those practice midterms. Okay, so let's see. Usually I give some general advice at these things. I don't know if I have much though. Main advice is don't worry about it. It'll be fine. Math is dumb. It doesn't matter. It's just a test. Also, the good thing about this quarter is that in comparison to usual quarters, tests are much less important. Things like homework and quizzes have more grades. So just get a good night's sleep, wake up, put aside an hour or two. It shouldn't take longer than that. Do your thing, go from there. And then if you haven't heard me say this enough already, when you sit down to write a solution to the non-multiple choice part, your goal is not to get the correct answer, right? Your goal is to convince me and convince Noah or convince Cameron or whoever is grading your exam that you know what's going on and that you can communicate the process. So when in doubt, show steps, give justification, stuff like that. So I don't know what I want to write for that. Show the process. / communicate. That's the main goal of math, is communication. What are we supposed to do for the midterm? Finish it. Do it, turn it in. I don't know if I, oh, like, well, so the untimed portion, you'll get a PDF probably that looks like the practice midterm, right? So you can just pretend that you were sitting there in class. You can pretend like nothing's different if you want and just write out your work, etc. Topics, mostly chapter 16. That's been covered a number of times, so I won't spend much time talking about that. Okay, so let's get warmed up with an example. Nothing too crazy, but we need to warm up a little bit. So are the midterms going to be the same? I don't know, to be honest. Maybe. They might be identical. They might be similar but slightly different. To be honest, I'm not sure. I don't have any official communication with the Cameron class. Okay, so like I said, we'll warm up with this example, get in the right mindset. What do we want to do? We want to set up an iterated integral which gives the area of some region, and that region's bounded by these curves. Y equals 1, y equals log of x, and x plus y equals 5. What's step 1 in any problem, math or not, in life? You draw a picture, if you can. But that's never a bad idea. Oh, this is log of x. Thanks. Yeah, again, my on paper handwriting is a little atrocious, so I'm doing my best. Okay, y equals 1. I bet I can draw that. That would look something like this. Log of x, I also know what that looks like. Maybe it'll look like that. And x plus y equals 5, what's that going to look like? You know, depending on how you want to think about this, you could think about this as y equals 5 minus x, which means it'll probably look something like that. Okay, and then if my picture is to be believed, I think that's the region. All right, we'll switch back to white. You guys win. How about that? Is that fine? Whoops. I should have made a poll for the background page instead. I guess I'm so used to, I'm like 100% dark mode everything. So I really dislike the bright white backgrounds. All right, so there's the region we care about. Now, first question we have to figure out, yeah, I have night shift on. I played around with the black background. Yes, you're completely right. I'm off to a terrible start that I didn't draw the natural log function correctly. Good catch. I promise I can probably pass 31B. Maybe not right now. So anyway, we probably hopefully get a region like this. And if I want to set up an integral which gives the area here, I'm thinking about, well, the area of this region E, what is it? It's the double integral of 1, right? Yes, you can attend, anyone in the world can attend my discussion sections. Unless you want to Zoom bomb me, don't do that. But you can come listen. So the area of any region is the double integral of 1 over that region. That's maybe the main thing to take away from week 1. Now, I want to turn this into an iterated integral, And the thing that stands out to me here is that when I look at this region, again, if my picture is correct, which we can figure out if it actually is, this is a horizontally simple region, right? Now, what does this simplicity mean? You want to think about this as being a consistent upper and lower bound. So it's horizontally simple because if I fix a y value and integrate like this, the lower bound is always given by this chunk here. The upper bound is always given by this chunk here. In contrast, this is not vertically simple because if I start integrating in the y direction first, well, here the upper bound would be given by this piece, the log of x. And there, I can't really see what I just drew, but the upper bound would be given on the right-hand side by this upper piece. So the takeaway here is that this region is horizontally simple. It's not vertically simple. So what does that mean? That means when I set up an iterated integral, I want to integrate with respect to x first. Okay, well, how do I get x bounds? I look at my picture and I identify visually the curves that define the bounds. One of them is this log curve. That gives the lower bound. And the upper bound is given by this guy right here. Now, the thing to be careful about is the lower bound is given by this equation, but I'm integrating with respect to x first, which means what? I need to solve for x. I need x equals something to determine the bound. So the lower bound is determined by y equals log x, which if I solve for x, this is like e to the y, right? And what about the upper bound? Well, the upper bound is given by this equation, geometrically. So algebraically, I want to solve for x just like I did. So the upper bound would be 5 minus y. Okay, now, I guess I should have thought about this for more than 3 seconds when I wrote the problem, but that's okay. How do we determine the y bounds? Well, geometrically, one of them will be given by this equation, which is 1. And then the other one will be determined by whatever this intersection point is. Because what do we do when we have an iterated integral and we want to move out of the layers? To determine the next layer of bounds, you take the region that you care about, squash it onto the y-axis, right? So when I do that here, when I take E and squash it onto the y-axis, I would get this interval. That interval determines the y bounds. The lower bound is 1, and then the upper bound, this is the part that might be a little silly. We would have to determine the intersection point of these two curves, which would be, maybe I'll do that in green to be color consistent. We could set, for example, y equals 5 minus x, and then x is e to the y. So this gives y equals 5 minus e to the y. And we would want to solve this equation. And like I said, if I had actually done this problem when I wrote it, I would have realized, I don't know if I can solve that equation. We could plug it into Wolfram Alpha. I don't really care. This is all about the process, right? So to solve this equation for y, I don't think I can do that here. So I'll just say we get smiley face. whatever that number is. That'll be our upper bound. All right, it's about 1.3. Now, we could do this computationally. Maybe one remark I'll make is that good to know that it's approximately maybe 1.3. But if you write 1.3 as the bound or 1.307 or something, that's wrong, right? A decimal approximation is not the same thing as the number. And almost certainly this number is irrational because there's like an exponential involved. So it's maybe approximately 1.3, but I would almost never use decimals ever. As long as you're in math class, don't use decimals. And yeah, once you become an engineer or something, then you can use decimals. But what do we do then? I would do exactly what I did here, which is whatever the solution of this equation is, I'll call that smiley face, and then I'll put it right there. Probably on a test, this kind of thing wouldn't happen because, you know, hopefully Noah worked through the problems that he writes. So I wouldn't worry about it too much. That's my fault for not doing the problems that I write ahead of time. So whatever that number is though, that would be it. And I didn't say do it, I just said set it up. So that means we're done. Okay, questions about that? That was our warm-up problem to get the kinks out.
Well, thank you. You're a real cool guy.
Jason thinks I'm a really cool guy. Thank you.
We all think you're a really cool guy.
Okay, if there are no questions, let's move on. Something more interesting. What do I have next? Yeah, the math midterm might be getting to people. Yeah, I guess make sure you're muted. Yeah, I mean, also you can ask questions if you want. Please ask questions anytime you want, but let's see. So if the region is only vertically simple, that means you must integrate dx first, right? You meant horizontally. Yeah. So if a region, in general, if you have a region which is horizontally simple, integrating with respect to x first is a good idea. Whereas if you had a region which is, say, vertically simple, but not horizontally simple. So what's a quick pictorial representation of something like that? This would be a region which is y simple, oops, but not x simple. That says simple. So I'd want to integrate with respect to y first here. Cool. All right. Here's my next example. I'll let you guys read this for a second, and then I'll read it out loud as well. But the whole past week, right, has been focusing on these change of variables maps and stuff. So I just have a couple things that I want to think about a particular map. So I'm giving us a map G of U and V. Now this map, it eats something in the UV world, and it spits out something with two components. And what we want to do is I want to think about this as being the X component, and this as being the Y component. So this is a map from the UV world to the XY world, which, you know, this isn't an integral problem, but this map G represents a change of variables map. And so one good thing to think about is, can I figure out what curves in one world correspond to in another world? So for part A, I'm specifically asking, I have a line segment in the UV world. You could write that if you want. If it were me, I would probably just say this, and I wouldn't worry about specifying things, but I guess you could write that if you want.
Yeah.
All right, some people still aren't muted. That's okay. We'll have ambient noise. Hey, Justin, could you mute yourself by chance? Yeah, so I thought about that, but I'm worried that if I mute everyone, will it like permanently mute people? Let's try it.
What?
Okay, there we go. Good idea. Anyway, so in part A, we have a line segment from 1, 1 to 2, 3 in the UV world. So I guess this would look something like this. And we have this map G, which is going to eat this red line and spit something out over here. And what we want to do is we want to figure out what we get when we're over here. What to do.
Wait, Joe, I just have a quick question.
Yes.
How do you know whether you're going from whether the original question is asking you to go from UV to XY or from XY to UV?
Well, so I'm picking that up basically from the notation of G. So when I write down G of UV, what that's telling me is that the map G goes this direction. Like the inputs are U and V, so the map has to go this way. So then anytime I talk about the image of something under G, it's talking about going this direction. That's a good question though, and you do have to maybe think a little bit, but based on roughly the variables that I'm using, the image of something is you always feed that thing into the domain of that function. Yeah, so if I wrote G of XY, it would be the other way. I think we'll try to not ever write something like G of XY. I think G will tend to always use as going from the UV world to the XY world just to be consistent, but yeah. Okay, so if you were Joe, how would you figure this out? So yeah, so G inverse would be like this. So Lean asked, UV is supposed to be simpler than XY. I mean, that's the goal when we do these variable change problems, yeah. So Ricardo's idea is plug in values of X and Y into G. I don't know if I want to do that because G eats UV things. Right, so okay, so there's a whole lot of ideas that are flying by super fast. Roughly that all seem good, but what we want to do is we want to describe this line segment in the UV world and then just plug that information in here. You could do this in a number of ways. If it were me, here's what I would do. But you could probably do other stuff. So if you want, try something else and see if we get the same picture in the end. If it were me, I would parameterize this line segment. So, now we've got to remember 32A. How do I parameterize a line segment? Well, I need a point on the line, which we've got, for example, 1, 1. And I need a direction vector. Well, I could get a direction vector by subtracting these 2 points, right? So for example, here's a parameterization of this line segment. R of t is, I start at 1, 1, plus, and then my direction vector would be 2 minus 1 is 1, and then 3 minus 1 is 2. So this comes from taking the vector 2, 3 minus the vector 1, 1. And then what is my parameter range here? Well, when t equals 0, I'm at this point. And when t equals 1, I'm at that point. So this is for t between 0 and 1. And then if I group these terms together, this is going to be like 1 plus t, and then 1 plus 2t. And so in the uv world, this is u, this is v. And I can use this parameterization to figure out, or it'll spit out a parameterization for the image. So the image has parameterization. What? Well, it'll be g of r of t, which is what? Well, what was g? I already forget. G was u squared minus v. Yeah, so some of you might be ahead of me already. You'll have to let me catch up. I'm a little slow. So u squared minus v would look like this. And then u minus v was the y component. So u minus v would be 1 plus t minus 1 plus 2t. So do some simplification. Let's see, what do we get? This is going to be 1 plus 2t plus t squared minus 1 minus 2t. And then here we get 1 minus 1, and then t minus 2t, which is minus t. And then here, these cancel out. That's kind of nice. So in the end, we're left with t squared and minus t, which is what Eric got. Eric beat me to it. And again, this range is from t equals 0 to 1. Okay. What does this mean? That's a parameterization of the curve. How am I supposed to figure out what this looks like? Well, what could we observe? This is x. This is y. So this feels a lot like a 32A problem to me, right? And the observation is that x equals y squared. So why is t from 0 to 1? Because that's how I defined my parameterization, roughly. So in the question, which you can't read anymore, I specifically asked about the image of the line segment. And so this is something to be careful about, that I don't care about the whole line, right? I'm specifically feeding in a segment into the function. So I need a way to describe very specifically the segment from here to here. So when I write down a parameterization like this, I need to specify a range for t values. And for this particular parameterization that I picked, those t values would range from 0 to 1. Right, so the points for this line segment, these are in the UV world. This is kind of what Katie was asking about earlier, which is like, if I read part A, how am I supposed to know that, right? like, how do I know if this line segment is in the XY world or in the UV world? And it's specifically because the domain of G is the UV world. And when I talk about something in the image of G, or what is the image of blah, 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 that means that I'm feeding something into the domain. So I don't say that explicitly, but it's kind of implicit that they live in the UV world. Okay, in any case, the Euclidean curve that we get, yeah, so a private question was, could I clarify what G is? In this problem, G is just a function. It's a function that eats something in the UV world and spits out something in the XY world. That's it. So for this problem, I don't mean anything other than that. So x equals y squared. Oh yeah, so how did I conclude that? This is the x component. This is the y component. And what I want to do to figure out what this curve looks like is I want to relate them to get a Euclidean equation. And here I just kind of get lucky by observing that, like, well, how is this related to this? If I took negative t and squared it, what would I get? I would get t squared. So in other words, I would get y squared equals x. And yeah, so this is a good point. We're not quite done because of this segment issue. We should, in our picture, specify the actual range that this curve passes through, right? So, you know, we could draw the whole x equals y squared curve, but that would be wrong. This is going to be a segment of this curve, right? And how is that segment defined? Well, at time 0, so the t values range from 0 to 1. When t equals 0, what point are we at? 0, 0. And when t equals 1, what point are we at? We're at the point 1, negative 1. So what that means, and I maybe should have done this before I drew these axes, so let me change the picture a bit. The image of this line segment is going to be the part of the curve x equals y squared from the point 0, 0 to the point 1, negative 1. And that would do it. That would be the image of the segment under this transformation. So there were a couple questions on the problem set for this week from like the early questions in 6.6 that were pretty much this kind of question where it was like, here's a transformation, here's something in the UV world, figure out the image of that thing over here. And this one is like a little more complicated than some of those questions, but the idea is the same. Whoops.
Hey, Joe.
Yes.
I was wondering, are the lengths of those line segments both the same? And physically, like if they are, like what's going on?
Nope, not necessarily.
Okay.
They could be completely different. Like for example, you know, maybe not this function, but what if, oh no. What if I had a function which just took the UV world and stretched everything out by like 1 billion, right? Then it would take this segment and stretch it out to like a super mega long thing.
Okay, so it's just based on how they're related, like with
Correct.
that formula out there. Okay, got it. Thank you.
Yes, and then a private question I got was just to clarify that the image under G, what does this mean? That means you feed the thing over here into G, and whatever you get out, that's the image. And then a question, could I summarize the steps for curve parameterization? In general, so for now I wouldn't worry about it too much. This will come up, parameterizing curves will come up a lot more later on. I would say for now, maybe just worry about parameterizing lines. And so how do you parameterize any line ever? You find a point on the line plus t times a direction vector. So this is how you describe a line. Or you could just use like a Euclidean equation. So I think the ideas that some other people had were like, well, what if I just found the equation of this line? You could do that. That's like a freshman year high school problem or whatever. You could somehow use that and then use this function and it would work out the same. So there's never one way to do something like this. This is just how I would do it. Okay, there's the image. And in part B, I just want the Jacobian. So this won't be too exciting, but I just want to make sure we all know how to compute Jacobians. Then we'll do more of this later when we do some change of variables problems. But the Jacobian of a map G, what is it? Well, it'll be the determinant of, and it's the determinant of the matrix of first partial derivatives, right? So in the top left corner, I'll take the partial of x with respect to u. The spot over, I'll take the partial of x with respect to v. And then in the second row, I do the same thing with y. And also, I'll remind you what this function was, so I don't have to keep scrolling back up. I think it was u squared minus v, and then u minus v. Something like that. So a private question was, if we would find the equation of the line, how would we go from there? So let's say that this equation was like y equals mx plus b, because I'm too lazy to figure out what it actually is. What would I do? Actually, sorry. Remove that from your brain. This would be v equals mu plus b, right? That would be the equation that you'd want to find. Then what do? Well, we have v solved in terms of u, so you could take that. Thanks. It looks like it's 2x minus 1. So it would be v equals 2u minus 1. You could take this expression for v, pop it up in here. And when you do that, you would get something involving only u. And that would be a parametric, that would be a parameterization of the curve with parameter u. And it should be the same in the end. But that's probably what I would do. I would take this expression for v and plug it into g and see what happens. And then, so the question again was, how do I know that t goes from 0 to 1? That's very specific to my parameterization here. So the way I decided to parameterize the curve, t ranges from 0 here, oh damn it, 0 here to 1 here. But if you parameterize differently, your t interval might be different. Anytime you write down a parameterization, you just want to figure out, where do I start here? Like, what time does that correspond to? And where do I finish here? So in my specific case, maybe just by plugging in some numbers, that's t equals 0 to 1. Anyway, so the Jacobian is the determinant of this matrix. So the determinant, or the derivative of x with respect to u, it's going to be 2u. X with respect to v is going to be -1. Y with respect to u is 1. Y with respect to v is -1. And how do we compute a determinant? It's this times this minus this times that. So let's see, we would get -2u minus -1, which is like +1. And I think I did that correctly. All right, so private question was, could I do number 3 from the extra problems that Noah posted on Campus Wire. Sure, we can do that. Look at that, I have it pulled up ready to go. Okay, so actually before I do that, good question. Good question. So the question was, wait, Joe, aren't you supposed to put the absolute value? In this question, what did I ask for? I just asked for the Jacobian. Now this is confusing, and it's mostly just a matter of definitions, so it's easy to get confused. When you change variables in an integral, the thing that you put in the integral is the absolute value of the Jacobian. So like if we were doing this in the context of some integral, when I used the change of variables problem, I would put in the absolute value. But the Jacobian is just this thing. So the Jacobian of G is literally just this. And so that would be my answer. And then, yeah, you should just leave it in terms of U and V. In general, it'll be a function of U and V.
Hey, Joe.
Yes.
I have a question. So does the Jacobian itself, like, does that equation mean that as you're moving further along, like the U axis, then that those points as they're translated onto the XY graph are distorted more? Like, what
Yeah,
is?
that's one way to think about it. Yeah,
Okay.
so positivity and negativity, I don't know. Noah hasn't really talked about this much, and I don't know if this came up in Cameron's class at all. But if the Jacobian is positive, that means that it's like orientation preserving. And if it's negative, it kind of reverses the orientation. Whatever that means, don't worry about it. You don't have to know anything about this yet. But yeah, that's a good way to think about it. Like when U is really small, when U is 0, the Jacobian is 1, which means the area is not changed at all. But then if I move like way in the negative U direction, so that U is like negative a billion, then the determinant would be like 2 billion. And so that means that it would scale the areas by like a billion. So that's correct. Yeah.
Okay, cool.
Let's see. Do we have to know the domain of U to find the absolute value? Yes. So in this case, it would depend on what the domain of U was. But since I didn't ask about anything in terms of changing an integral, we don't have to worry about that. Yeah, so we'll talk about orientation later in the course. It'll be really important for the kind of second half, but for right now, we don't have to worry about it. Okay, where'd that go? So here's one of the problems that Noah posted on Campus Wire as an extra, something extra to practice. And 3 and 4 were pretty tricky, I think. I haven't done them yet, so we can see if we can, maybe I'll just flounder and fail, and then you all can laugh at me. Anyway, so what are we doing? This problem wants us to calculate a double integral over some region D, and that region is bounded by some curves, as always. Y equals x plus 1, y equals 1 over x, and y equals 2 over x. Okay, so I'll let you brainstorm while I sketch a picture of this region. Yeah, so I got a private message about a suggestion that Noah made, and that's correct. So I'll show you what that is in a sec. But it should be said, and this is important to keep in mind when you're doing this change of variables thing. I said this at the end of discussion today for those of you guys that were there, but I think it's intimidating a lot of times when you get these problems and it's like, oh my God, like how do I find the correct substitution, or like how do I figure out what to do? You can do whatever you want. This is the same thing as with a U substitution in single variable calculus, right? There's no correct thing to do. There's just helpful things and unhelpful things. But if you want to call U e to the x minus 2 cosine y, go for it, right? It might be dumb and it might not be helpful at all, but you can do it. As long as you're consistent, you can do whatever you want. So there's probably multiple variable changes here that would be helpful. This one is tricky. So and as Noah said on Campus Wire, probably this question as written is a little too difficult for an exam. So you can keep that in mind. Finding the correct variable changes is a little nasty. And we'll do some simpler ones later. Oh, what was I doing? I was going to draw this curve. That's one of my mantras. Okay, so one of these things is y equals x. Y equals x plus 1. It's going to look like that. Y equals 1 over x. We'll do this. Probably looks like that. And then y equals 2 over x probably looks like this. Yeah, and so then the question is like, okay, so what if I'm doing this problem and I just have no clue what to do and I can't get anywhere? Could I split this up into like 1, 2, 3, 4, so maybe 1, 2, 3, 4, 5, 6, 7, like up to 8 different regions? You could. It's probably the last thing I would do, and depending on who's grading, they may or may not be happy with that. But if your end goal is to compute the integral, yeah, I mean, you could just split this up if you want. Okay. Anyway, here's the region we're integrating over. And we want to find a change of variables map over here. So let me show you something that I think is tempting and would probably work. And then I'll show you the kind of thing that Noah suggested on Campus Wire is maybe like an alternative substitution. So here's something tempting to try. Well, what if I look at these two equations? I could write this as y minus x on the one hand equals 0, and on the other hand equals 1. Those are the two boundary conditions given by these equations. So those two equations generate an inequality like this. Fair enough? Likewise, here there's another really natural change that we could do. If I multiply both of these by x, I would get like xy equals 2 and xy equals 1. And so then I have some inequality like xy is between 1 and 2. That describes the region, whoa. This describes the region in the xy world, and then you say, ah, well, that's really nice. I could just call this thing u and this thing v. Try it if you want. What gets hard is finding G inverse. I mean, you can do it. But it's a little ugly. So what do I mean by that? Let me talk about this more carefully. So let's go down this route, see what happens, right? Maybe this is what we want to try. So if I let u be, what did I say, y minus x, and v be xy, I say, good job me, I found a change of variables, but yes, thanks. So this means G inverse, the inverse of G. So this is what I was going to explain. You know, this is great and all, but eventually we're going to need the Jacobian of G. And we're going to need to rewrite the original function in terms of u and v, which means more or less we're going to need to figure out this map G. So what we have right now, what does this variable change describe? This is saying, oh, sorry. Yeah, I think I misspoke. Finding G is ugly. Thank you. Someone privately messaged me. This right now describes G inverse. Why? What are these equations saying? They're saying that if you give me an x and y value, it'll spit out u and v, right? So give me x and y, and it'll spit out u and v. Give me x and y, it'll spit out u and v. What's happening on the picture up here? That would be giving me an x and y and spitting out something in the u and v world. That's what G inverse does. G inverse goes from the xy world to the uv world. That's what we've got here. Like I said, ultimately what we need is G. So I say, okay, that's fine. I'll just figure out G. And I'll do that by solving for x and y. So to get G, let's solve for x and y. This is the part that's like a little awkward. You can do it, but like what would I do? If I had to, I'd probably take this first equation and then I'd get like y equals u plus x, and then I could plug that into the second equation.
Hey, Joe,
Yes.
could I ask you a quick question? So in the book, there was like a question where we found the Jacobian by first finding the partial derivatives of u in terms of y and in terms of x, and v in terms of x in terms of y, and they inversed it.
Yeah.
Would that be something that works here?
Maybe. So I will say, I think you guys, so for anyone in Cameron's class, it sounds like you guys have maybe talked about like how to deal with the inverse Jacobian. We haven't talked about that in Noah's class yet. So that kind of thing will come later in this week. I would try to avoid that for now since we haven't talked about it. And you always have to be a little careful when we do that. So for now, I'll punt on that and I'll say maybe stay tuned. You could try here if you want though. Yeah. What am I doing? Oh, right. Sorry. I'm already losing my mind. So, you know, if I tried to do this, I would get some equation like this, but then I'd have to solve for x. How would I do that? Probably the quadratic formula, because this is a quadratic in x, and then it's like, oh, that sucks. So you could keep going down this road, but I think once you start doing this, it's kind of like, oh, this is a little ugly. Again, you keep trying if you want. If you want to ignore me, please do and try it. I'm not saying it won't work. I'm just saying it's a little ugly and there might be something a little simpler to do. This is why this one is really tricky. And this is why I think probably on a test, he would have to tell you, like, by the way, use this substitution. So Trina asked if I could try it. I really don't want to. Maybe later, if we run out of things to talk about, I can do it. I tried earlier, and once I got here, then I was like, nah, I don't want to do that. Yeah, so Ricardo's got the good suggestion, which is what if instead of this, we do something a little different, which is, and I'm going to need an extra page. Duh. Which is what if instead, what if I let u be, so oh, so actually Ricardo was a few steps ahead of me, maybe. Maybe that's what ends up happening. Here, I'll say what I was going to say. And this is, I think, more or less what Noah suggested online. And it might be the same as what you have, just a few steps ahead of me. I'm going to stick with this as being u. So let me let u be y minus x. Is that what I want to do? Probably. But instead of calling v x times y, what if I call v just say y? Let's try this. You could choose x as well. Yeah, probably. You could probably do like x equals or v equals x or something. Again, there's a gazillion things you could try. I think this might be helpful. So we have a couple still correct inequalities. Like these two inequalities still describe the region. Yeah, so the good question, and the reason why this is so tricky is, where do I get that from? This is going to be a little hard to describe. I'll try to do my best. Roughly, okay, so Ricardo's idea had a slight problem. So roughly, when I make this substitution, this is motivated by these two lines, right? So when we call u y minus x, we're kind of straightening things out in this direction. And then we also tried to straighten things out in this direction, but it didn't quite work and it got a little wonky. Or, it could work. But instead of trying to straighten things out in both directions, I'm only going to straighten things out in this direction. So I'm going to take these two lines and kind of force them to be like this. And then I won't touch the other stuff. I'll just like move things down here. And then whatever this does, I'll just let it do its thing. And then I'll get some region maybe like this. That's extremely vague and relies on a lot of kind of sophisticated intuition. So if that doesn't make sense, I wouldn't worry about it too much. Like I said, I think you'd have to be maybe told a substitution here. So anyway, I pulled this out of somewhere, who knows where. Let's see if it works. So the region D is still described by these two inequalities, right? Y minus x is between 0 and 1, and xy is between 1 and 2. And so what do we need to do? We need to ultimately determine what the bounds in the UV world are. Anytime you make a variable change, what do you have to do? You have to change the bounds. So I need to take this information, which is algebraic information in terms of x and y, and I want to convert this into UV information. Wow. So for this new substitution, I'm going to let v be y. So v up here in the thought bubble, whoops. In the thought bubble, I tried xy, and it seemed like it got a little hard. So this is kind of an alternative path that we're going to go down. And I will just let v be straight up y. Anyway, so what we want to do is we want to take this information, convert it into UV information. Well, the first one's easy, right? Also, probably shouldn't be 0, it should be 1. First one's easy because y minus x is just u. So this first inequality turns into 0, u to 1. That's really nice. Oh yeah, thanks, Eliana. Okay. Good catch. What about the second one? We need to figure out how to write x, y in terms of u and v? Well, x, if I solve for x in this equation, this would tell me that x is y minus u. Fair enough. And then what is y? This isn't what I want to do. What am I missing? Y is v. Oh, right. Sorry. Y is v, so y minus, yes. Thanks, Julia. I was missing the super obvious step. Math is hard. This is what happens. So x times y is v minus u times v, right? So is this any better? Maybe. We would get an inequality like this. Now, what do I want to do? Yeah, I don't know if this is any better, actually.
Wait, Joe,
Yes.
if you do it the way that you showed at first, but then
Yes.
we didn't do, you don't actually have to compute the inverse of the function at all. All you have to do is compute the inverse of the Jacobian, and then
Does it work out?
yeah, and then the because it's just gonna be. Oh wait, hold on. Never mind.
Maybe. I can't see it in my head. I feel like it might be complicated though. Yeah, this problem kind of sucks. It's kind of hard no matter what you do. So what we'd have to do here is we'd have to solve for v. Again, I'll repeat this. If you're watching this and you're like, what the hell is happening? Don't worry too much. I don't think anything this complicated will come up. Questions 3 and 4 that Noah wrote were pretty tricky. We'll give this a few more minutes of effort, and then if it doesn't clear up nicely, we can come back to it later. I want to make sure I do some maybe more straightforward stuff. But this is a quadratic equation in V, right? So we could complete the square, something like this. We could, let's see, I would want to add u squared over 2 and then subtract u squared over 2. That would give me 1 is less than. This now factors as v minus u over 2, quantity squared, minus u squared over 2. And so then I can go there and solve for v. And so I don't really think this is any better. It's about the same. We'd get something like this, and then I could root both sides. We'd have to think about positivity and negativity. It's probably positive, though. We can come back and think about that. Whoops. Could you try v equals x plus y? You could. I don't know. Yeah, I don't know if that would help. You could try. Unfortunately, I think no matter what you do, this is ugly and complicated. Sort of a lose-lose situation. In any case, this is a lot of algebra in one go, but if you simplify this thing, we would finally get an interval of v values, which would look like something like this. That doesn't look great either. Yes. Thanks.
Wait, Joe,
Yes.
towards the top, where did you get the 2u square over 2 from? And then u square over 4.
So I'm completing the square here. And I took the coefficient in front of v, divided it by 2, and then squared it. And then I did that incorrectly, and I got u squared over 2. And so I should have gotten u squared over 4. But yeah, I'm just completing the square here. Good catch.
Thank you.
Yes. I'm adding too many 4s. Yeah, we're about to dip out of this problem too, because like I said, I want to make sure that I do some actual insightful problems.
Do you think we could do like a problem that has the G inverse, but is just not as hard?
Yes. Which is, okay, so we'll come back to this. It's hard no matter what you do. Yeah, and on Campus Wire, he said that this one's too hard. So, well, 3 and 4 I have pulled up here, but I'd rather work on other stuff first, so we can, if we get really bored later, we can come back to these. But yeah, a problem like this I think is much too difficult. Let's do a simpler version of that. Oh, that was, let's do something like this, maybe. This will be much simpler. And then, okay, so let me look at a couple questions first while you guys think about this. For integrals where f of g of uv is easily determined, is it necessary to solve for x and y and use implicit differentiation instead? Whatever you do, your Jacobian has to end up in terms of u and v. That's the summary of all this stuff, is that do whatever you want. If it's correct, that's fine. But you have to get a Jacobian in terms of u and v. So if you can do that from trickery, go for it. If not, then no. So like, I don't quite know what you mean by use implicit differentiation, but ultimately, if you can get a Jacobian in terms of u and v, you're fine. And then Julius asked about a problem set question. Yeah, we can do that one at some point. Let's do this one first for fun. This will be a much more straightforward change of variables type thing. Okay, and as always, there's a couple ways we can think about this. If I'm looking at it, well, first of all, the problem doesn't say anything about changing variables, right? I kind of spoiled maybe how to think about this, but we could just think like, could I just do this? Could I set it up as an iterated integral and go from there like a normal person and not worry about any of this change of variables stuff? Probably not. Roughly just because if you were to set this up as an integral without changing any kind of variables, something like sine of x squared is very difficult to evaluate. And yeah, so you guys are correct that the region that we care about, this is an ellipse, right? So as always, the first thing I'll do is I'll sketch a picture. Probably looks like, doesn't even really matter, it's some ellipse, kind of. Yeah, and so that's a good idea. This is a change of variables problem to me, and there have been a couple good ideas, which is like, you know, if we were in an alternate world and this was like sine of x squared plus y squared, then we could say like, ooh, that's a polar coordinate problem and go from there. And that would be a good idea. The problem is it's not x squared plus y squared. So yeah, so David, I think you guys have a good idea of the flow of the question, which is, if you want, you could try polar coordinates as written, but it probably won't work well. So here's my thought process. Maybe I'll write this down here. Feels polar-ish, but not exactly. To use polar coordinates effectively, I would want something literally like x squared plus y squared. And the fact that we've got some goofy ellipse stuff happening here and here screws it up a little bit. Yeah, and so a lot of you guys have the correct idea, which is what if we make a preliminary variable substitution, which kind of takes this ellipse and squishes it into a circle. And yeah, so what we'll do is we'll do a variable change, which turns the ellipse into a circle in the UV world. That's one way to go about doing this. So I would like, so first, let's do a variable change to get this ellipse looking thing to look like u squared plus v squared. And then after that, we'll use polar coordinates. That's vague, but that's why it's in a thought bubble, because it's just intuition. So ultimately, I want a circle over here. So you guys tell me, what do you think our variable change needs to be? Yes, so yeah, so we could do a number of things, but I do like the suggestion for u equals 3x and v equals 2y. Roughly what I'm looking at is I look at this equation and I think, gee, I wish this looked like u squared plus v squared is less than 1. Wouldn't that be great? If only. Well, how could I force that to happen? I just want u squared to look like this. So therefore, u would have to be 3x. Likewise, v would be 2y. That's probably what I would do. So I would start off by saying, let me let u be 3x and v be 2y. Then the region, whoops, nine x squared plus 4y squared is less than 1. That's what's over here. What does this turn into in the UV world? This corresponds to, well, u squared is exactly 9x squared. So I've got u squared plus v squared is less than 1. So with this change of variables, the corresponding region is over here. Okay. So the next thing that I just want to remind everyone is how do we actually change variables in a double integral? Because I don't think we've actually done that yet tonight. So really quickly, just to recall, if you start out with a double integral in the xy world and you change variables to get a uv integral, you've got to change the bounds. You also have to change the function. The fancy way to write that is to say, well, look at f of g of uv. But again, this is just a fancy way to write change the function. That says function. This just means change the bounds. And then what else do you have to do? You have to change the differentials. How do we do that? This is where the absolute value of the Jacobian comes in. And then you get dA in the UV world. And yes, so writing f of x of uv, y of uv is the same thing as writing this. So that's changing variables. And you know, the one thing I want to point out, many of you guys listening right now, I know, had me in 31B in the fall. And I guarantee you heard me say many, 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 many times, when you change variables, what do you have to do? You have to change everything. You have to change the bounds, you have to change the function, you have to change the differential. Nothing's changed from 31B. We just have more variables to keep track of, and changing the differentials becomes more complicated. But this really is just an extension of doing a U substitution. Okay. So we can figure out how to describe the bounds, or redescribe the bounds. We've got a circle. We can change the function easily enough, and then the next thing that we need is the Jacobian of G. Now, like before, this describes G inverse, right? Why? Let me repeat that thought process. This description here says, if you give me an x and y, I'll spit out a u and v. So give me an x and y, spit out a u and v. We want the Jacobian of G, which goes this way. So that means to find G, I want to solve for x and y. So to find G, now, unlike in the previous example, this is a little bit easier. X is u over 3, and y is v over 2. That was a tough one. Okay, so in other words, what we've shown is that g of uv is, the first component is u over 3. The second component is v over 2. Then the Jacobian will be easy enough to compute. So the determinant of the matrix, the top left corner, will be the partial of x with respect to u is going to be 1/3. X with respect to v will be 0. V with respect, or y with respect to u will be 0, even though my v looks like a u. And then y with respect to v will be 1/2. A third times a half is a sixth, so the Jacobian that we care about is 1/6. Okay, so to implement this change of variables nonsense, what do we get? The original integral that we cared about was over this ellipse of sine of 9x squared plus 4y squared, dA in the xy world. By this change of variables formula, now I'm integrating over the unit disk in the UV world. That's what we figured out up here. How do I change the function? Well, sine of this, this part changes into u squared plus v squared. So I get sine of u squared plus v squared. And then I've got the absolute value of the Jacobian, which is just the absolute value of 1/6. So I get 1/6. And then dA in the UV world. And there's one step. So what we've done is we've done a change of variables to convert this into something over a unit disk and into an integral that looks like something that polar coordinates can handle extremely well. So having done that, unless there are any questions about that so far, like I said, much easier variant of this changing variables in the G inverse stuff than in the third question that we did. Get a sip of water. Oh, I forgot about my dinner. Okay, I'm cool with cold pasta. Okay, so what scent is the candle? Read this last night. It's called Vineyard Retreat, Cabernet with pear and mulberry. Okay, so let's move on. Yeah, I'm very sophisticated. I wish. Now we can do polar coordinates. Now we're doing polar coordinates with u and v, right, instead of x and y, but it works exactly the same. I'll let u be r cosine theta and v be r sine theta. Now, question, what is the bound for r going to be? Since we're describing a unit disk, the bound for r for any angle theta will just be from 0 to 1, right? The bounds for theta, I want to go all the way around the circle, so this will be 0 to 2 pi. I'll get sine of u squared plus v squared is r squared. And then dA in the UV world, after we change to polar coordinates, I pick up another Jacobian, which is the extra r. And then we're in the home stretch. We could go from there. I hate doing this. Did I say evaluate it? Yeah, I did. All right, let's just finish it off. I don't want to be the guy that just says, yeah, you can do it from here. Where did the 1/6 go? Good question. It disappeared. Thanks. I'd get a -1. All right, so let's do it really quick. I would now do a U sub where I'd call, say, S R squared, and ds is 2r dr. This is going to turn into r dr is 1/2 ds, so this is 1/12, 0 to pi, 0 to 1, because when r is 1, s is still 1. This will be sine of s, which looks kind of weird. All right, I'll speed through this. Oh God, antiderivative of sine is negative cosine. Then that's constant, so I just pick up a factor of 2 pi. So on the small chance that I did this correctly, you probably get that. You can check me if you want. Okay, so a decent question is, do I need to make this U sub explicit? I'm going to give you a non-answer, which is I would. Do you have to? That's maybe something at this point that you could skip. That's probably fine at that point. So I would say if it were me taking a test tomorrow, I would, but you do you. You could probably skip over that. Okay, scroll up. I don't know if that's good, Sarah. You can let me know. I'll take another sip of water and let you soak in what we just did. Yeah, so instead of, maybe later, I'll come back to 2A just because I've talked about that one a lot with various people over the past couple of days. Let me do something a little bit similar though. I wrote a problem myself, which is reminiscent of that. Because of my shitty handwriting, it actually looks the same. Might look like sine of 2 theta, but this is sine squared of theta. Maybe let me make that a little clearer. But this will be similar to 2A from the practice midterm. Whoops. What was the answer to the previous problem? Something like pi over 6 times 1 minus cosine of 1. Question 3, practice midterm 1, part C, y is theta negative pi over, yeah. I'll talk about that one in a second. We can come back to that one. If you're on, Maddie, if you're in Noah's class on Campus Wire, I have a post that explains this, maybe post 76, something like that. But there's a couple answers on campus. We can come back to that one also. This one will be a little similar. Oh yeah, thanks Alfred. Okay, I was right. Post 76, I think I answered that one. Okay, so what do I have here? Consider some curve r equals sine squared of theta in the upper half xy plane. And I want to do a bunch of stuff. For example, in part A, I want to sketch the graph, and then I want to set up some integral to compute the area, and then who knows what else I want to do. But let's think about part A first, sketching a graph of this curve. Now this is a little similar to to that question from the practice midterm for the following reason. Maybe I won't get ahead of myself. But here's some general advice. So let's say you're given a polar equation and you need to graph it in the XY world, as in that midterm question. Probably the first thing I think about trying is maybe I can just convert this into a Cartesian equation and then go from there, right? Like for some of these equations, like we've been able to just convert them into circle equations, and then we can see like, oh, this thing's a circle or whatever. So maybe first try converting to Cartesian. But sometimes that won't work. That midterm problem with sine of 2 theta, that's an example where I don't think it works so well. And also here, I don't think it works so well to do this either. And we can think about why that's the case. But in that scenario, if you have something that does not translate to Cartesian equations very well, what do? Roughly, I would just think about plugging in some points and thinking about the general qualitative behavior of the curve. Pick some theta values, track the position of the curve, and generate your sketch that way. Feels a little wonky to do it, but you know, it's really the only thing to do at this point. So if that fails, if converting to Cartesian doesn't really help you, maybe just plot points and think about the qualitative behavior. Which again, that's vague. What do I mean by that? This is what I mean. So the curve is r equals sine squared of theta. In a thought bubble, let's just see if we can convert this to Euclidean equations in any reasonable way. And so then the question is, how accurate do our graphs have to be? I wouldn't worry too much about accuracy, but just as long as they pick up the general features, I think you're fine. You know, the other reason why this is a little bit silly, and it still feels weird, I'm not used to giving this kind of advice, but what would I actually do? Yeah, just plug it into like Wolfram Alpha or something. Like Wolfram will graph these for you. And you, I mean, try it yourself first. It's a good idea you should think about these things yourself, and you shouldn't rely on technology, but you shouldn't not use technology either, right? So think about it, and if you get stuck, you know, plug it into Wolfram or something else, and it'll confirm your suspicions. But I think as long as you pick up the general important features of the graph, I think you're fine. I wouldn't worry too much about accuracy. In any case, we could think about how to convert this into Cartesian equations. Because I have 2 copies of sine, if it were me, I would want to multiply by r squared. You get something like that. But then this is weird. This is like x squared plus y squared to the 3/2 equals y squared. And then what? I mean, we've converted it, but like, do I know what that looks like? No, I don't know what that looks like. So this doesn't seem very helpful. So this didn't work. So what would I do before I plug it into Wolfram Alpha? I would just recognize, well, where am I supposed to plot this? I'm supposed to plot this in the upper half plane. What does that tell me about the relevant angles that I care about? The angles that define the upper half plane are 0 to pi, right? So the fact that the problem says upper half plane means theta is going to range from 0 to pi. you know, in some of these other problems, he's said something like blah, 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 blah in the first quadrant. The first quadrant is cut out by 0 to pi over 2, etc. Or if he said like the third quadrant, which he wouldn't say. I don't know why anyone would do anything in the third quadrant, but if he did, he would say, you know, what would that mean? That would mean pi to 3 pi over 2, etc. Anyway, so I care about angles from 0 to pi, so I'll just, you know, we could do a couple things, but I'll just plot some points and I'll think about the general feature of this curve as theta ranges from 0 to 2 pi. And we could even do a couple things, like for example, we could draw a region in the theta r plane. Here's 0, here's 2 pi. Sine of 0, sine squared of 0 is going to be 0 squared, which is, yay, which is 0. Still getting used to this. Also, I know that, oh, why did I write 2 pi? Sorry about that. I only care about pi. Sorry, 2 pi. Sine of pi is also 0, so sine squared of pi is 0. And then, you know, as theta ranges from 0 to pi, what does sine do? Well, the y value goes up until it hits 1, and it hits 1 at pi over 2. 1 squared is 1. And then it goes back down. So sine squared from 0 to pi doesn't really look a whole lot different than sine, right? It'll look kind of like this, maybe just exaggerated a little bit more. There's my beautiful drawing. Now that's not the drawing we want, right? What are we supposed to do? Sketch a graph of the curve in the xy plane. This is in the theta r plane, so it's not the picture we want, but it'll help us figure out the qualitative features of the curve in the xy plane. So the picture that we actually want is in the upper half plane. Now, if I translate this information here into this information over here, what do I get? Well, at an angle of theta, which means I'm angling in this direction, how far do I walk? I walk 0 far, which means I stay put at the origin. Now, what if I go to like an angle of pi over 4? When theta equals pi over 4, whoops, I meant to do sine squared. Sorry about that. You guys can please always yell at me for dumb mistakes that I make because I'm losing my mind. Sine squared of pi over 4 would be 1/2, I think, which clearly is right here. So what that means on this picture is that when you angle out at pi over 4, how far do you walk? You walk 1/2. So I'm going to put that right here. And then at an angle of pi over 2, how far do you walk? You walk 1. So that would kind of look like maybe right there. And then at 3 pi over 4, it'll be at a height 1/2 again, which will be here-ish. And then once we get to pi, we're back at the origin. So something like that. Maybe that's what we get. And again, maybe after I do that, I pop this into Wolfram, see if it looks roughly like that. And if it does, then I pat myself on the back and I move on. The sketch like that is probably good enough for a problem like this. And this is exactly what I would do to graph like sine of 2 theta in the first quadrant, which is what we have to do on the midterm. I would go through the same process, etc. Any questions about that? That was part A. Where'd my water? Oh, there it is. It's probably fine if you just show the graph itself. You know, I don't think it's a bad idea to have a picture like this. Noah's really placed an emphasis on when we do these different variable changes and stuff, having both of these pictures. It's definitely a good idea. I don't know if you have to do it, but I think if you have a picture like this and then a picture like this, it's probably fine. So if we get negative values, do we just ignore them? Not necessarily. You know, this kind of thing came up on the quiz the other week, not the last quiz, but I think the previous quiz, where he gave you a curve where r was negative, and you need to consider that. It's a little goofy, but I'll say it probably won't happen tomorrow. Okay. Anyway, there's my sketch. What else do we need to do? Part B was set up an iterated integral which gives the area of the region contained in the curve. Okay. So that region is this stuff. This part won't be so bad. So, damn. So for part B, we need the area of the red region. What do you guys think? As a double integral, it'll be the double integral over the red region of 1 dA. And then we're probably going to use polar coordinates, right? It's a polar equation, so it seems like it makes sense. So let's convert this double integral into polar coordinates. dA yeah, so Joshua's got the right idea that, you know, we'll convert this into polar coordinates. Every time we do that, we pick up an extra r from the Jacobian. Then I'll probably do dr d theta. What are the r bounds going to be? Well, if I meander over to my picture here, you know, it's kind of staring you in the face, but why is that the upper bound? It looks like all of the rays that I care about start at the origin. And I walk, walk, walk until what? Until I hit the red curve. So that means my lower bound is probably 0. And the upper bound, excuse me, is given by that red curve, which has equation r equals sine squared theta. So that's the upper bound. And then what about theta? Okay, no one has any ideas, or everyone's tuned out. Thanks. Yep, 0 to pi, just, you know, we're in the upper half plane, so what angles do I care about? I want to swoop out from here to here. To trace out the whole curve, 0 to pi suffices. Now, Um, that would do it. We don't actually have to find the area. I just said set up an integral, which gives the area. So there we go. Cool. The more interesting part is part C, which you can't see. What does part C say? Similar thing, except now I want to set up an iterated integral which gives the area contained by the curve, but also above the line y equals 1/8. Okay. So let me sketch picture again. Oh, that was terrible. That's okay. There's my balloon shape, but then I've also got this line y equals 1/8. And the region that I want to find the area of is the stuff inside the circle, but above this orange line. So we'll have to think a little bit harder now. So let me call this E, maybe. So just like before, the area of E is a double integral. As always, it's just the double integral of 1 over that region. And I want to convert this into polar coordinates now. So again, I'm going to get r dr d theta. What we'll have to be a little more careful about now is what are these bounds? So what's the deal? Now, when I start walking from the origin, so if I fix an angle and walk this way, what determines my lower bound for r? So I walk this way, I walk, walk, walk. The first time I hit the region is when I hit this orange line, and then I walk until I hit the red line, right? So the rays that I'm integrating over now look like this. What that tells me visually is that the lower bound for r is determined by the orange line. Let me write that down. So visually, the lower bound for r is determined by the orange line, which is y equals 1/8. Somehow I have to translate this into an algebraic bound for r. So what do? I just take this thing, which gives me the lower bound, and I convert it into polar coordinates. How do I write y in terms of polar coordinates? It's r sine theta. And then I'm looking for an r bound, right? So what do? Just solve for r. And there's my lower bound. Upper bound hasn't changed, right? Because the upper bound is still cut out by this red curve, and that's the equation there. So upper bound is sine squared of theta. So before we think about theta, this is a good general thing to think about. I've talked about this in discussion, but for those of you guys that are listening to me for the first time this quarter maybe, or whenever, a good general strategy when we're thinking about polar coordinates is draw a decent picture of your region. And to think about getting bounds, think about walking along these rays and identify visually based on your picture the piece that determines your lower bound and your upper bound. So usually using your visual aid, I identify that the orange piece is what determines the lower bound. So I take the algebraic data for the orange piece and turn it into algebraic data in polar coordinates. That's the general process, which is going to work like most of the time here. Okay, and so now we need, yeah, so private question was, when will I post this recording? Hopefully pretty soon afterwards. You know, like if this ends up being like a 5-hour video file, I don't know how long it's going to take YouTube to upload a 5-hour video file. It might not take that long. I don't know. But after this ends, I'll look into getting it ready to post. So hopefully by tomorrow morning. I'll also, on my website, I'll post this. Oh no, I'll post this document as well. So could I give an example, or could he, maybe referring to Noah, could he give us an example that isn't R simple? That was a private question. Maybe. I'd be surprised. I think almost certainly the kind of thing I would expect on the test is a region which is R simple. Usually those are the kind of things that polar coordinates are good for. So I think if the intention is to use polar coordinates, it's probably going to be R simple. Maybe not, but probably. Anyway, so I just rambled about, you know, how do we determine bounds? You use a picture to identify the visual data, and then you use that visual data to determine the algebraic data. We need to do that with theta too. Now, unlike in the previous part, theta is not going to be from 0 to pi. Victor said pi over 6, and that might be correct. I haven't done this in my head yet. But the angles that we care about now are determined by these intersection points, right? When I think about the angles that I'm swooping out, I start at this intersection point and I finish at this intersection point. So the visual data that determines theta are these intersection points. So what do I do? Oh, yeah, I lost my train of thought. So what do I do? So maybe let me write this down. Visually, yeah, we could, so there's a number of ways to think about it. I'll show you what I would probably do. I would say visually, theta bounds determined by the intersection of the red and orange curves, written in green. So how do I compute that intersection? Well, here's the red curve. Here's the orange curve, written in black, right? But we took that orange curve and turned it into polar data. So set them equal to each other. R equals sine squared theta, but it also equals 1 over 8 sine theta. So that intersection in polar language is defined by sine squared of theta equals 1 over 8 sine of theta. And then what do I do? What am I trying to find? A theta bound. So just like I did over here with R, I just algebraically solve for theta. This turns into sine cubed equals 1/8, which means cube root of 8 is 2. So sine of theta is 1/2. And this is where the pi over 6 comes from. Sine of pi over 6 is 1/2, and also sine of whatever this angle is, you know, pi minus pi over 6. That'll be the upper bound. So therefore, theta is pi over 6, and let's see, it would be 5 pi over 6. Those will be the bounds. Sorry for squishing that in there a little bit. And if you can read that, That would do it. Okay. So that was a little trickier than the previous part. So what would happen if we set theta from 0 to pi in this scenario? And then, yeah, we'll talk about, well, I'll do that kind of thing next. I'll talk about some kind of triple integral and simplicity in 3 dimensions. So what would you do, or what would happen if you set theta from 0 to pi? You would just be incorrect. But then what would you be integrating there is a decent question. It's a good thing to think about. It will be undefined. So this is actually kind of a fun thing to think about. But so let's say, right, yeah. So maybe before I say that, Caitlin, I'll come back to your question. Let's say I pick an angle beyond, or like smaller than pi over 6. So like pi over 30 or something like that. What does this describe? It describes the orange line. So the bounds for the integral would be the red curve to the orange line. So if you integrated from 0 to pi, you would be integrating over slices like this. And as you get closer and closer to 0, like Elijah pointed out, you're going to be integrating off to infinity. And you'll probably pick up, well, I mean, the same thing will happen over here. Something fishy will happen, but it'll be a little wild. So, okay, the question was, what if I found the area of the entire region and then I subtracted away this area? That would be correct as well. I think it might be, it'd be correct. It might be harder, it might be the same difficulty, not sure. Okay, so then another question, whoops, was, how do I know when it'll be 0 to pi versus when you have to solve for the theta bounds? So the answer to that is it depends. The answer to like 95% of questions in 32B are it depends. But so the real answer is I claim that you do always have to solve for the theta bounds. In the first part, the way I did that was with words. So by that I mean that the part of this problem that told me in the first part that I care about angles 0 to pi was this right here. So sometimes you'll get problems where the information about something like theta is going to be determined by a word. Like it'll be in the upper half plane or like in the first quadrant or something like that. You know, so for example, if they say in the first quadrant, well, I mean, it depends, but it comes down to, I don't know if that's helpful at all, but it comes down to identifying some kind of phrase like this that tells me upper half plane, so therefore 0 to pi. But really, there's no getting around drawing a good picture. The other answer that doesn't sound very helpful in the moment, but it is really important is, you know, it's tempting to be like, come on, Joe, like what if I'm, you know, visually impaired and I can't draw a picture like this? Like, can I do this problem without drawing a picture? Maybe, but you need to kind of embrace the geometry. I think a lot of people understandably, you know, geometry is hard. Like understanding this visually is difficult. And there's some crazy things that happen in the class, but one of the things that Noah's been trying to emphasize is that, you know, like it or not, visual intuition is really important. So I think having a good picture, and being able to use that picture to identify visually, you know, where these things are determined, it'll be difficult and you may not like that answer, but I think it is important. You've got to just close your eyes and fall back into the geometric intuition. and trust that you'll land on a soft bed eventually. Might take a long time, but eventually you will. Okay, any other questions about that one? Let's see what else we've got here. I want to do one involving like a Z simple region or something. Okay, so this won't be Z simple, but this will be the kind of concept that you should know about this stuff. So let's do this next. Okay, so what did I write? I don't even remember anymore. Set up an iterated integral which gives the volume of the region bounded by Z equals 1 minus x squared and x equals 3 minus y squared minus z squared in the first octant. Okay. I'll let you guys think about this for 30 seconds and I'll eat some more of my cold pasta. In particular, given a problem like this, carbs for life, the first question you want to be asking when you think about, okay, I need to set up an iterated integral, is you want to ask the question, is this region I care about simple in some direction? Like, is it x simple or z simple or y simple or whatever? So that's the first thing to be thinking about. So okay, so a couple questions in the chat. Should we have to know the formal definitions for like simplicity? No, I wouldn't worry about it so much. I would know what they mean, but I wouldn't worry about like, if I held you up against a wall, like, could you write down the formal definition? Will we ever get questions about octants other than the first octant? Probably not, no. Almost certainly it'll be always in the first octant. Ricardo thinks it's X simple. Maybe. We'll think about it. I don't even know where the other octants are located. Like, I don't know how to number them other than the first one. So you probably won't get anything not in the first octant. And then, so Joshua's got a good question. Yeah, so a couple of you guys think it's Y simple. I agree. I'll draw a picture in a minute. But Joshua has a good question, which is like, you know, what's the deal with technology? Can't I just plug this stuff into GeoGebra or something? Yeah, you could. And you probably should. Now, my answer to this stuff is going to be, I think it's important to be able to think about this yourself. And I kind of mentioned this earlier, but you know, I wouldn't necessarily rely on technology as a crutch. Like, if your first instinct is to look at this and, you know, if I ask the question, what's step one here? And your answer is GeoGebra. I think it's important to have some visual intuition, even though we have access to technology, just because it'll help you later on down the line, not only in this class, but in other kind of math classes in the future. But you should use technology. I mean, it'll help you. Like, I would think about, we'll try to think about this ourselves first, but I encourage you to graph these things. You know, I'm going to try to draw a picture and it's going to suck. I'll tell you that right now. And so when you look at my shitty picture and it's like, Joe, that's not helpful at all, graph them in GeoGebra and, you know, play around with the picture and it'll make more sense. So you should use technology, but you shouldn't rely on it. It shouldn't be a crutch. It should just be something that helps you out. Okay, let me actually draw something. Now, there were a couple good suggestions in the chat, which is, Yeah, John's identifying something which is important, but again, I wouldn't rely on this. Is that he's identifying that it's probably wait, I'm confused. So now I'm worried that I wrote down a silly problem. I think I meant to write something different down. So this might be way harder. So Ricardo, I think I brushed off your comment about X simplicity. So I'll say for now that I think I meant to write, for fun, let's try the problem as written. But I think I meant to write this. That's my bad. If this is too hard, then we'll come back to it. Let's try it as written first. So actually, let me go back to John's comment that I was going to point out. And this is sort of what Victor's asking about, was just like, are there any algebraic indications for simplicity? Sometimes there are. And for example, one of the things that John observed is that in this equation, there are no y's. That kind of thing is an indication that it might be y simple. The other indication is that, you know, here we could solve for this in terms of y as a function, and that's another indication of simplicity. So yes, there are algebraic indications for simplicity. I wouldn't rely on them, but maybe let me write this down, because it is helpful, and you should have a balance of algebraic and geometric intuition. So if you can solve for smiley face in two of the equations, in maybe exactly two of the equations, it might be smiley face simple. No guarantees. And I wouldn't think about it like this. I would draw a picture and I would think about it. But that's an algebraic indication that, that we have simplicity. Now, you say, hang on, Joe, you said in exactly two of the equations. I only see y in one of the equations. What's the deal? Or anyway, so maybe we're thinking about the hypothesis that this is y simple, for example. I counter with, there are actually three more equations that we need to consider here that I didn't write down. I said in words in the first octant. What does this mean? This means that x equals 0, y equals 0, and z equals 0 are also part of the boundary. Let's go purple. And 1, 2. So I can solve for example, y in exactly two of the equations might be y simple. I can also do that with x, right? X equals 0. Or no, I can't. I've got 1, 2, 3 x's here, so that's a little awkward. I've also got 3 z's. So that's a little awkward. So algebraically, the indications here are that this might be y simple. So the algebra suggests y simplicity. Let's ignore this for now. But again, I'm not going to use that as the basis for my argument, and I think it is important to sketch a picture. So let's do that. So what does z equals 1 minus x squared look like? Well, in the first quadrant, it would look like that. And then, as has been pointed out, there's no y dependence, so I just kind of stretch forever and ever like that. So again, in the first quadrant, this would kind of look like that, maybe that, something like that. Yeah, I think this will work okay. It'll be a little weird, but yeah, again, I don't think this is what I actually wanted to do, but it's okay. What about this thing? What does this look like? So Joshua, I don't know if I understand your comment. I think I would agree. I think I'm agreeing with you, I guess, is that, yeah, like this is some kind of parabolic thing moving in the y direction. Yeah. Okay, so what about this other green thing? Well, so this is actually kind of important. This feels pretty similar to one of the homework problems that we had due a couple weeks ago. Yeah, Aiden's got it, which is that this green thing is going to be like a parabolic blob with like base at x equals 3, and then it kind of opens like this. Now this point right here is x equals 1, right? So it is sort of an important feature that here is clearly where 3 is, and it's beyond that thing. Yeah, and then, you know, Josh was also pointing out is that for this green shape, when you look at the trace in the YZ plane, it's going to be a circle, exactly. So kind of what happens here, if it were me, those two things that I just drew are supposed to be the traces in the XY and the XZ plane. And then we'd get something like that, sort of. And the part that I won't be able to draw very well is these, so this green blob, this like parabolic looking thing, and this red sheet, they intersect in some weird curve, like here maybe. It's a little hard to see exactly what it looks like. But I don't know, maybe it looks something like that. So the green thing is not part of an ellipsoid. The way you want to think about this picture is that it kind of keeps opening like this, and it would also go like that, and it would also go down like that. But I only care about the part in the first quadrant. So these traces are like hyperbolas or parabolas, and then this part is the circle that you're identifying. All right, in any case, I'm pretty proud of that picture, TBH. Let's go gray. Oh, I don't know if it makes sense to you guys, but the region that we care about is contained in here. And with our picture, it's a little easier to confirm that this is y simple, right? So if I think about this region and I think about y simplicity, what would that mean? That would mean I fix an xz value. So maybe like I start here, and then I walk, 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 walk until I hit something. And the thing that you'll always hit is this green shape, right? That's kind of the lid of this region. So visually, the lower bound in the y direction is this piece, and the upper bound is this piece.
Just a quick question.
Yeah.
Isn't there like another region in the first octant bounded like on the outside of the red and inside the green?
Yeah, that's a good point.
Do we just like
So,
ignore that for now?
no, that's a good point, and that means that I wrote a shitty question. And so, what I think that was Aiden is pointing out is there's actually another region, and that's a good point. Let's say, um, bounded above by this. Hopefully that makes sense. But no, you're absolutely correct, and that's my fault. So if this came up on a test or whatever, and if it was written exactly like that, and you identified it, like, hold on, there's actually two regions, that would be something that you could go to Campus Wire and be like, no, no, like that's a valid thing to ask about. So thanks for pointing that out. I didn't think about that. I was thinking about, well, I don't know what I was thinking about because I don't think I meant to write this originally. So who knows? But I guess I've decided that I was thinking about this region. But you are correct. There is like a sliver out here. Thanks. Yeah, so that other region, I don't know if you can tell, but it'd be like the ring, the part of a ring, like sitting outside the red thing, but then inside the green thing. Yeah. I was going to say something, but I forgot. Oh, right. So I was going to say, like, I think Alonzo asked earlier about, like, should we know the actual definitions of simplicity and stuff? No, I wouldn't worry about the mathy, scary looking definitions, but you should know what it means. And what does it mean in words? Or how do I think about simplicity? Do you have a consistent lower bound and a consistent upper bound? In other words, in the y direction, the lower bound is always given by this piece, and the upper bound is always given by this piece. So there's a consistent lower bound and a consistent upper bound. In contrast, here's a question, which is not relevant for what we're doing, really, because we've decided it's y simple, so we could just move on. But for the sake of thinking about this, here's my question. Is this region z simple or x simple? I kind of indicated when I was talking about the algebra here that maybe not. But I'm curious what you guys think. Now that we have a masterpiece of a picture to look at. It's a pretty good picture. It's probably like maybe top 30 math pictures I've ever drawn. I've drawn a lot of math pictures. Okay, what would my top 5 pictures be? I don't know. I'd have to think about that. Okay, so let me spoil it. It is neither x nor z simple. Why is that the case? Let's think about maybe z simplicity. I think that might be a little easier to spot. So question, when I think about z simplicity, I want to fix an xy value and walk in the z direction. What if I do that over here? So fix an xy value and walk in the z direction. Where do you stop? You stop when you hit the red thing. So here, the upper bound is the red piece. But what if I'm like over here? There's a region here where when you start and walk up, what do you hit first? You hit the green piece. Uh-oh, that's an indication that this is not z simple. It's maybe a little, you have to think about the region a little bit. You know, thinking about these things is difficult, but there's a portion here where the upper bound is given by the red chunk, kind of like here. But then there's also a portion where the upper bound is given by the green chunk here. So it's not z-simple. And for pretty much the same reasoning, it's not x-simple either. Oh, I don't know. So for example, if I started here and walked, eventually I would hit the red piece. But then over here, if I walk, I'll hit the green piece. So in the x direction and in the y direction, there's not a consistent upper bound. Anyway, that was fun. So you don't have to go through all that, but it's good to think about. The upshot is that this region is y simple. And not z simple or x simple. Any questions about that so far?
I have a question about at the beginning. You changed it to have y equals 3 minus x squared minus z squared, and then you said that because that equation and y equals 0, you can solve both of them for y, then it may be y simple. How did you like do that, but now the equation you're using is the other one, or was that just an example?
That was just an example in that case. But actually, not really much has changed. Almost nothing has changed. I can say what I mean more about that, but like the red thing that I erased up here earlier,
Yeah.
if I had actually replaced this equation with that, this picture would look pretty much the same, actually. It'd be a little different, but it would look the same. The main features would be the same, and so it would still be y simple. It would still not be x or z simple. If you want, you can think about that, but the difference is going to be that in this iteration that I've erased, it was a lot easier to solve for y. It was like already solved for y, and here we just have to do some algebra, but it still won't be hard.
Okay, so you'd have to take like a positive or a negative after you do the square
That's
root.
what we'll have to do. Yeah, exactly.
Okay, got it. Thank you.
And then so Ricardo asks, so is drawing the region usually our best shot at finding simplicity? Yes, I would say in any problem like this where you have to set up an iterated integral over like a three-dimensional region, try to draw a picture for sure. Anyway, so the volume of this region, well, what is it? Abstractly, it's the triple integral of 1, which I want to convert this into an iterated integral, and I'm not going to worry about the outer two bounds yet. I'm just going to take care of the inside bounds, which are going to be with respect to y, because that's where the simplicity is. So I'll do dy first, and then we can figure out what to do with the remaining variables after that. What will my y bound be? And so this will address, Eric, I think what you're asking about. Visually, the lower bound is determined by this piece, right? Well, what is that piece? That's the xz plane, which has equation y equals 0. So the lower bound is 0. What about the upper bound? Well, visually, the upper bound is this cap, which is determined by the green thing, which my color coding is confusing, so sorry about that, but the green thing is this equation right here. Now, the green thing determines the upper bound, but I want an upper bound in terms of y. So what do? I just algebraically solve for y here. And like Eric pointed out, we're going to have to take a square root. So let's see if I can do this in my head. Did I do that right? I think so. And the question is, which square root do I care about? And why? And that wasn't a rhetorical question. Yes, I care about the positive one. Yeah, exactly. I care about the positive one because we're in the first octant. The y values are positive. So specifically care about the first or the positive square root, and there's my upper bound for y. So yes, good question was like, what about that original thing I wrote? What would that look like? I claim it would look almost identical. Like if I drew a picture of that region, it would literally look the same as what I just drew. I mean, it wouldn't be the same, but with my poor drawing skills, it would literally look the same. The features would be pretty much identical. You could think about that if you want. But the picture would be almost the same. Okay, so we're still not done because we have to make sense of these X and Z regions. But so what do we do from here? So I mentioned this earlier, but to determine the next layer of bounds, when you set up an iterated integral like this, what do? You take your whole region that you care about and you squash it onto the new direction of interest. So here, the new direction that we care about is the XZ plane. So what I'm going to do is I'm going to take this whole region and squash it onto the XZ plane. Dogs are going wild outside, which would give me that region. Yeah, so Ricardo's pointing out that the projection is exactly determined in this case by this red curve, which is z equals 1 minus x squared. So let me draw that. So here's the projection of region onto the xz plane. XZ, this red curve here is going to look like this, and I've got boom, boom, and there we go. Now we just have to think about how do I set a double integral over this region up. It's both z simple and x simple, so we could do either. I think it's probably more natural to set this up as a z simple region, like integrate like this, in which case the lower bound is going to be given by z equals 0, and the upper bound will be given by 1 minus x squared. So I could set this up by doing dz first, and then dx. And we'll go from 0 to 1 minus x squared. And then finally, I take this region, squash it onto the new direction of interest, which is the x-axis. And what do I get? I get the interval from 0 to this point will be 1. Now do it. And hopefully I just said set up. Yeah, good. I don't want to have to do this. Okay, there we go. There's an integral that gives the volume of this region. You could easily flip the order of z and x with no problem as well. But because this is y simple and not x or z simple, I do think you'd want to do y first. Yeah, so how do I know it's y simple? I think the best way to think about this is going to be based on the picture. So when I think about simplicity in any direction, you want to ask the question, is there a consistent lower bound and a consistent upper bound? In other words, is there a lower bound given by one smooth piece and an upper bound given by one smooth piece. And in this case, in the y direction, there is, because as I integrate this way, in the y direction, the lower bound is given by this single smooth piece, and the upper bound is given by this single smooth piece. So the fact that each of the lower and upper bounds are a single smooth piece, that's what indicates that this is y simple. You know, then if you want, you can think about this like there's some algebraic indications, like here we can solve for y, here we can solve for y, and I can do that exactly twice. But I would be a little careful with that, and I think in general it's better if you can get a good picture. And again, this is the kind of thing that you could for sure graph, and you probably should graph in GeoGebra to confirm that you've got the visual intuition correct. Yeah, we can do something like that at some point. Let me see what else I have here. I'm going to give preference to the problems that I wrote just because, you know, those are the things that I wanted to talk about. But then later on, we can do something. Okay, let's switch it up a little bit. I want to make sure I do a problem like this, and then we can do some other stuff. And maybe I'll take crowd suggestions after this one. Yeah, I want to make sure I do this one. Then we'll move on to other stuff. Okay, so what do I have next? Compute some iterated integral. Okay. Pasta time for me. I'll let you think for a sec. Now, you know, it's not such a big deal, I think, in a class like 32B and compared to something like 31B, but, you know, many of you have heard me say this kind of thing a lot at this point, but I'll say it again while I eat. Pasta's very cold, but it's almost gone, so it's okay. So in case you haven't heard me say this 40 times over the course of this year, it's really important to keep in mind that when you sit down and do homework from 16.4 or whatever, you have all this contextual information of like the problems in 16.4, I'm probably going to use 16.4 techniques. Or when you flip open 16.6 and you're doing problems, it's probably going to be 16.6. Or when you're working on the homework from the week that we talked about polar coordinates, you're probably going to use polar coordinates, right? But on a test or in real life or whatever, you could come across an integral like this, and I don't know where this came from. I don't know what week this is from, right? You don't have any context, and this can make problems hard, right? I think it's less of a deal in 32B, like I said, than in some other classes, but it's still something to consider. I didn't tell you what to do here. I'm just saying, compute it. Now, Wolfram Alpha could compute it easily, but it's the process, right? Any ideas?
Change, switch the order of integration.
So you guys have some good ideas. So maybe I look at this and I'm thinking, okay, what's in my toolkit? Maybe I can just like literally straight up evaluate it. Maybe I don't have to do anything fancy and I can just, you know, turn the car on and go. But if I did that, looking at this integral with respect to x, this looks really scary. So because of that, I toss that out and I say, I probably don't want to integrate this as written. So what else could I do? What else is in my toolkit? I could change the order. I could do polar coordinates. I could do some ridiculous change of variables. Or I could quit and move on. The simplest of those options, well, is quitting and moving on. But beyond that, probably changing the order of integration is helpful. So yeah, we'll definitely draw a picture of the region that we care about, but maybe the idea here is that, all right, also I've got to, been sitting in the same position for like 3 hours. Let's switch it up. Oh, right, what was I saying? But the observation is that this is really hard to do with respect to X, but with respect to Y, pretty easy, right? So the thought process is maybe it's easier to integrate. To do Y first. And then if that doesn't work, then we can start thinking about other options that we have, like who knows what, right? Or we just move on, like we did with problem 3 from Campus Wire earlier. Okay, so this is a decent question, which is like, does separation of variables apply here? The answer is no, because of this. So separation of variables applies when you integrate over a rectangle. So if this is like 0 to 1 and 0 to 1 or something, then you could completely decouple these into two different integrals. But because of this lower bound depends on y, you can't really decouple anything yet. So separation of variables strictly applies when you're integrating over rectangles. Okay. So I want to switch the order. I want to do y first. So what do? I just take this and then I put it here and then I'm done. Nope. That gets you a 0 out of 10. What do we have to do? Every time you want to rewrite the order of an integral, you have to start from the beginning. And you have to redraw the region and think about simplicity and blah, 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 do this kind of thing that we've been doing. There's sort of there's no great way of getting around that. So the first thing I'm going to do here is sketch a picture of the region. Okay, let's see. Well, what do the inner bounds tell me? The inner bounds tell me that x ranges from root y to 1. So one of the bounding equations is x equals 1, which that would probably look like this. The other one is x equals the square root of y. What does that look like? I guess that's the same thing as y equals x squared, right? So that maybe looks like that. And then y goes from 0 to 1. So here's y equals, whoops, that's x equals 0. Y equals 0, y equals 1. So therefore, the region that we're integrating over is this guy right here. Okay. So, big whoop, what does that mean? Well, if I ultimately want to switch this, whoops. So like I said, my goal is to write this as blah, 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 dy dx. If I want to integrate with respect to y first, then I'm integrating slices like this, right? The lower bound here in the y direction is going to be given by the x-axis, which is y equals 0. And the upper bound visually is given by this curve right here. Now I want to solve this in terms of y because I want a y bound. And so what would that be? That would be y equals x squared. And then what? The corresponding x bounds, I take this region and I squash it onto the x-axis. I would get the interval from here to here, which will be from 0 to 1. Okay, so good question was, right, so a good question was, how do I know that it's not this region? How do I know that it's this region? Because root y is the lower bound. So the way I would think about this is that this initial inside integral here that told me that x is between root y and 1. Root y is here, 1 is here. The region between them is this stuff. If it were this region, the original integral here would have been from 0 to root y. That would have given me that region. All right. Good job, Joe. We've successfully changed the order. Now we can cross our fingers and hope that we can actually evaluate this. So with respect to y, that integrand is easy, right? This will just be y squared over 2. Plug in x squared in 0. When you plug in 0 for y, everything goes away. So we'll get x to the 4th over 2x cubed e to the x squared dx. And then once you know, x's cancel out, I get 1/2 x e to the x squared. And that's something I can do. So earlier the question was, do I have to do the u sub or can I do it in my head? I can't do it in my head. Let's see if I can. You probably pick up an extra factor of 1/2, so I'd get a 1/4 e to the x squared at 1 and 0. Probably get something like that. That was a little fast at the end, but you know, at that point, it's just good old math 31B at this point. Okay, that was fun. Any questions about that one? I'm getting Facebook messages at the wazoo. One sec. So good question. What if switching the bounds didn't work? I don't know. I mean, so it depends. Like, for example, let me do one more of my prepared ones, actually. It could mean that you should just do something else, like maybe tripolar coordinates or something. But in general, it's hard to say. Hard to say. All right, while we're on a roll, let me knock out another one of these. And then I'll take fan suggestions. Okay, it's a good question. Has Cameron posted anything about the midterm? This one I think will be relatively quick. But same deal as before. And again, so this is kind of a, you know, along the lines of Victor's question, which is like, well, you know, what if something like that doesn't work? Or if I get some random looking iterated integral like this, what do I do? What do you think? 0 to 3, negative root 9 minus x squared, root 9 minus x squared of that stuff. Elijah thinks polar, so does Jessica. I agree. I've taught you well, or someone has. So why might I think polar? To me, there are two major indications. Thanks, Elijah. I don't know if I'll take all the credit. I'll take some of the credit, though. Yeah, exactly. So in my opinion, there's always two major indications that you should use polar coordinates. One of them is if you ever see circular regions. And like Ricardo's pointing out, that's pretty much exactly what we have going on here, right? For example, this inner integral gives us a y bound of, for example, y equals root 9 minus x squared. That's part of a circle, right? Square both sides, blah, 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 blah. This is x squared plus y squared equals 9. So that's a huge indication that polar coordinates might be good. The other indication is if you see, for example, in your integrand, x squared plus y squared. Exactly. So Anne is pointing out, in the integrand, we do have x squared plus y squared. It's hiding a little bit, but if you factor out the x here, you'll get x times x squared plus y squared. So anyway, these are two kind of major indications that suggest that polar coordinates are a good idea. All right, so let's do it. What's my first step? Picture. Yes. It's a little more awkward on Zoom asking like questions to the class, because normally in person I'd be like, what's the first step? And then within a second, you all would be like, draw a picture. And now it like takes you time to, you know, type out draw. So it's a bit of a delayed response. Thank you though. Okay, so the inside integral tells us that y ranges from negative blah, 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 blah to positive blah, 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 blah. And the outside bound here tells me that x ranges from 0 to 3. So if I sketch this region, you know, I did this up here already, but when I think about these boundary equations, these are both telling me that this is part of the circle x squared plus 9, x squared plus y squared equals 9, which is a circle of radius 3. Now, I can also see from my x bounds that I only care about the right half of this circle, right? Because x goes from 0 to 3. So here's x equals 0. You know, here's x equals 3, but that coincides with the radius of this circle. So it looks like the region we care about is this semi-disk. thing. And thankfully, very easy to describe in polar coordinates. So I'm too lazy to write out the original integral. So I'll just say original integral equals, let's convert this thing to polar. What do you think about theta? I think negative pi over 2 to pi over 2. Because I'm swiping out angles like this. And what would r be? Well, r is determined by this equation right here, which turns into r squared equals 9, which is r equals 3, because what I'm doing is I'm integrating over radii like this. And so Jessica's got a good question, which is, wait a second, isn't this an angle of 3 pi over 2? Yes, it is. And it shouldn't matter. So you could say, well, so it depends. Like, right, so whatever you do, you'd have to be careful. Like if you want the lower bound to be 3 pi over 2, you should probably make the upper bound can I do math in my head? 5 pi over 2. And that would work. You should get the same answer if you do that. If you wrote the lower bound is 3 pi over 2 and the upper bound is 5 pi over 2, you'd be in business. Now, if you wrote 3 pi over 2 to pi over 2, there you're getting yourself in trouble, because 3 pi over 2 to pi over 2 would be going in a direction like this. And that's not the region we're interested in, right? We're interested in this side over here. So you could start at negative, or you could start at 3 pi over 2, but you want to be consistent. You want to make sure that you clock out this region. So you'd want to go up to 5 pi over 2 in that case. Or you could do what I did and start at negative pi over 2 to pi over 2. But yeah, it's a good question. Okay, and then what happens here? Well, this guy, factor out the x. This is x times x squared plus y squared. So what do we get? X is r cosine theta. X squared plus y squared is r squared. And then from the Jacobian, I get r dr d theta. And then again, as usual, this is hopefully a relatively straightforward thing to do. I'll blaze through it. You guys can take a mental break. So I've got r to the 4th. When I integrate that, I'll get r to the 5th from 3 to 0. Which is 3 to the 5th. Oh God, who knows what that is? Don't know, don't care. So I'll write 3 to the 5th. And then integrating cosine theta gets us sine of theta, evaluated at pi over 2 is 1, 243. Thank you. So I'll get sine of pi over 2, which is 1, minus sine of negative pi over 2, which is negative 1. So 1 plus 1. So that's 2. So 243 over 5 times 2. Another one down. Okay, so could you use separation of variables in this case? Yes, because now once we get here, we're integrating over a rectangle. Yeah, so this is a scenario. I don't really think it helps much. Like, it doesn't really change anything, but that is correct that you could decouple into an r and theta integral separately, and it'll more or less work out the same. Nice. Another one down. Okay. Now what? Now I take a bite of pasta. done. Oh, what was private question was 1 plus 1. Yeah, I kind of blazed through that part at the end. This just came from integrating sine or integrating cosine, which is sine of theta evaluated at pi over 2 and negative pi over 2. So that's where the 1 minus negative 1 comes from. Okay. A long time ago, someone asked, where is it? I think Julius asked about a textbook problem. I don't know if he's still listening, but we can do that one. I forget which one it was.
I was gonna do that one you just had on there.
Oh, this one? This one's kind
Yeah.
of boring. We can do that one if you want.
Oh, it's boring.
It's not that hard. If you want to try it, you want to take a mental
Okay.
screenshot of it really quick. And then,
Would it just be, it's just like 1 minus x, and then like
Yeah.
1. And then you just like plug in numbers basically, I guess.
yeah, pretty much.
Yeah.
Okay, so then there was a question, wouldn't it be sine when we integrate cosine? Yes, I think that's what I wrote here. So can I do a brief Fubini's theorem problem? To me, that's what something like this was. So we can do more later. We can come back to that. But I think in terms of Fubini's theorem, this is the kind of thing that I would expect from this example. If it were me, I would do this one next. This is another change of variables kind of thing, but it's a little different than what we've done so far. But if you have strong objections, or if you guys want to do something else, I can't remember what Julius's problem was, so. Oh, I didn't mean that, Katie. I don't think you have a boring taste in math. It's a good problem. I wouldn't have written it if I didn't want it. Okay, so 2 people, 3 people. That's a rousing majority of the, wow, we still got 100 plus people, damn. All right, let's look at this one. I'll let you read it for a second and maybe I can finish my pasta off like 4 hours after I made it. So I've got a rectangle in the UV plane. And I'm giving you a transformation, and D is the image. Yeah, you guys are really here to just watch me eat pasta. I know what you want. You only want one thing. Anyway, D is the region of this rectangle in the XY plane. And so I want to sketch that region and then evaluate a double integral. pasta. Yeah. Okay. Whoops. All right, 1 sec. I'm getting really warm, so I'm going to turn on a fan. Yeah, so Ricardo's asking, R is in the UV plane. This is similar to the issue that we talked about in the very first problem, where I don't specify that explicitly, right? I'm not telling you that, but implicitly, the image of this under this map, I look at this and I think the domain of G is the UV world. So that means to take the image of this thing must live in the UV world. Okay. I'm going to turn on a fan real quick. Oh, yeah. Yes, this word is map. Function, if you rather. Okay. So let me get my sketch going. You guys can get a head start on me as well. So what we have is in the UV world, I have a rectangle. And this function is spitting things out into the XY world. What am I doing? I don't even know what I'm drawing. So 1 to 4 would look like this. And what we need to do is we need to figure out in part A, what do I get over here when I feed this square to G? Okay, so how do I do this? Now, if you're sweating and you're thinking, uh-oh, he's going to do this parameterization nonsense again, we don't have to. This kind of scenario is a little different than the very first one I did, where I think because the segments that we're mapping are just vertical and horizontal, I think it's more straightforward to just use the Euclidean equations. And I wouldn't, you could parameterize if you want, but I wouldn't necessarily worry about that. So in other words, here's what I would do. I would identify, for example, this lower line here. What's the equation of that line? It's V equals 1, right? Okay. So how do I determine what happens? No, yeah, exactly, you're right. So how do I determine what happens under V to that line? I just restrict G to V equals 1. So consider G of U comma 1. This would be restricting to V equals 1. Well, what do I get? So I go up here, I look at G. If I set V to be 1, I'll get U squared and then 1 over U. We've got to figure out what this looks like. So we did this a little bit already. What could we observe? This is X. This is Y. How are these things related? What if you square Y? You would get 1 over X squared. Sorry, you'd get 1 over U squared, which is 1 over X. So this tells us that X is 1 over Y squared. So this is going to be kind of a goofy looking picture. I'll try to do my best. And if you want, we could think about this as being Y equals 1 over the square root of X. That would be the Cartesian equation, which is parameterized by this parametric curve here. I'll let you think about that for a second while I graph this. And if there are questions about that, let me know. So do we plug it in only when we don't know how to do it otherwise? I don't know if I know exactly what you mean. No matter what you do, you have to plug in this data into the function. You could do that like this, or you could do it parametrically. You could do it various different ways, but like whatever you do, it's ultimately going to be the same thing. That probably didn't answer your question, so if not, you could try again if you want. But maybe a more direct answer would be like, if you can just plug in the equation and it makes sense, that's maybe a good thing to do. And if it gets more complicated, you could think about doing something parametrically, but if you can do this kind of thing, may as well. Okay, so what is this going to look like? Ooh. That'll be my Y equals 1 over root X. Whoops. And then we'll just continue on. For example, what about this other line? This top one, this is V equals 4. So if I consider G of U comma 4, what do I get? I'd get U squared over 4. And then 16 over U. And this will be similar. We'll just have to work through the constants. So this is X. This is Y. Let's see. This will be, so how do I get Y? I take did anyone do it for me? My brain isn't working anymore. So let's see, what if I do, so if I do 1 over the square root of X, that would be like 2 over U. So then I need to multiply that by 8. I think that's right. So that curve would be, I don't know, maybe that. If I take this first curve and multiply it by 8, it'll kind of smoosh it up. So there's like a 50% chance I did that right. But those are the these lines, and now we need to move on to these lines, and then we'll get our image. So it'll be pretty much exactly the same thing. I'll do it a little quickly. For example, this line here is u equals 1. So if I consider g of 1 comma v, what do I get? I'll get 1 over v, and then v squared over 1. So how am I doing the conversions from uv to xy? Yeah, so I'm not explaining this step very well. If you mean going from here to here, I'm just kind of getting lucky and noticing the observation, but here's a better way to do this. So let me, instead of randomly pulling this out of somewhere, let me do this a little bit more methodically, because that was confusing. Sorry about that. These two things here tell me that x is u squared over 4. And this way we can check that, see if I was actually right. And y is 16 over u. What if I solve for u in both of these? There I would get, u equals 2 times the square root of x. And here I would get u equals 16 over y. Well, then if both of these are equal to u, I can set them equal to each other. And there's my Cartesian equation. So I could simplify it to, I think I was right, y equals 8 over the square root of x. Okay, so Alex has a good question, which is what about the negative sign? What about the negative sign? What do I know about both x and y? Here's x, here's y. First of all, what do I know about, so what do I know about u and v? U is between 1 and 4. V is between 1 and 4. In particular, u and v are both positive. So therefore, x is positive, y is positive. So when I take square roots, I do genuinely just care about the square roots, the positive square roots. But that is something to check. So it's a good question to ask, and you should be asking that question because there is something to think about that. Is there any indication that we have to parameterize for a problem like this? So again, I have a feeling I may be misunderstanding the question, but my answer to any of these questions involving like finding the image of something under a map, the only way to do that is to parameterize, in my mind. Generating parametric curves like this is in the way I'm thinking about this is like literally the only thing you can do. It may not seem like it based on what I'm doing, but I would say that if you have to find the image of anything, you want to think about the boundary curves, and typically when you feed the boundary curves in, you'll get parametric equations. So similar to Matthew's question, I have a feeling that probably didn't help. So if not, you can let me know. I can try again. Anyway, let me figure this other one out really quick. So this looks like x squared is 1 over y. All right. Yeah. I mean, okay, so here's the other thing you can do. And this maybe isn't great advice to give as a TA, but I'm pretty serious about it. Let's say you take a test, and you open up the test tomorrow, and you flip open to a question, and you read it and you're like, oh my God, I have no clue what's going on. Like, I remember Joe did something crazy and I didn't get it, and now I have to do it myself and I'm scared and I don't know what to do. Just skip it. Just like, don't do it. You'll maybe lose 10 points or something. It's fine. It's not going to matter 5 years from now. You'll be fine no matter what happens. So don't worry. You'll be fine. You know, you should probably try the problems if you want. But if you get a problem and you can't do it, I don't think any less of you. Okay, so that's y equals 1 over x squared. Now, this is a little tricky in terms of sketching this region. The rough shape of 1 over x squared looks kind of like this, but it's different, right? 1 over x squared will decrease faster. So, you know, my picture is not fantastic, but when I draw 1 over x squared, it's going to look like that, kind of. In contrast to something like 1 over root x. And then I suspect that when we look at the final side here, which is u equals 4, what do we get? I keep forgetting what g is. 16 over v, and then v squared over 4, which is completely symmetric to what we had over here. So the same thing will happen with the variables flipped, right? So this will be let me not try to be fancy, let's just do it. X, y. So v is 16 over x. So v squared is, I don't want to do this. And v is also 2 root y. So 16 over x equals 2 root y. And so how do I want to think about this? Y is 64 over x squared. I think I did that. Which clearly in the picture looks like this. Questionable scaling, but you get the idea. And if you have to draw a picture like this, that's the kind of liberties you should take. So I haven't done any of the other problems. We can talk about 1 and 2 if you want. I think they're more reasonable. I'll punt on 3 and 4 until, if I'm still going at like 11, then maybe we can go back to those, but I really wouldn't worry about those, and I'd focus on 1 or 2. We can talk about like the first or second one after this if you want, yeah. Anyway, what was I saying? If you actually graph these curves in like Wolfram Alpha or GeoGebra or something, it looks kind of crazy. It's like super stretched out, and it's pretty hard to see actually, which is one of the benefits about being able to understand this stuff yourself without any technology crutch, because you can kind of take liberties with the scaling to get this picture. What was the last curve I graphed? Yeah, so I should have drawn that down. That was this guy down here that you couldn't see. So from this last equation, or from this last restriction, I generated y equals 64 over x squared. Which again is completely inaccurate in terms of the scaling, but it's the kind of thing that you'll have to do. All right, so there's my beautiful picture of this region. Any questions about that? It's probably the hardest part of this question. You know, next we'll evaluate an integral, but I think finding the image here is more difficult. Okay, so can we use this process of holding either the u or v constant for any problem going from uv to xy? Well, not necessarily, just because the thing over here in the uv world, it might not consist of lines for which u and v are constant, right? So for example, this first one that I did like 10 years ago, wherever it is. Oh yeah, the thing over, whoops. The thing over here in the UV world that I was feeding in, this is definitively not of the form like u equals a constant or y equals a constant or something like that. So in general, you might have to be a little careful.
Joe,
Yes.
for that one that you just pointed out, I noticed that you could have plugged in, like, for example, the point 1 1 into the equation for g of uv, and you still would have gotten the points 0 0, and then if you did
Correct.
the same with the 2 3, you would have gotten 1 -1. Is that like correct? I guess.
Yeah, I mean, that's a good observation. So, you know, if I plug in the point 1 1 here, I get 0 0. I agree. And then if I plug in the point 2 3, you probably get the point 1 -1. You better, or I screwed up somewhere. And so what that tells you is that, well, this point gets sent here and this point gets sent here. That's great. But without doing all of this nonsense that I did down here, what happens in between, right? I mean, you know, it's not like you can connect them with a straight line. That would definitively be incorrect. And so specifically because this is a non-linear transformation, so the tough part is just, so you can identify the endpoints that way. That's a good thing to do, I think. And then you'll just have to do some work to figure out, you know, does it go like this? Or does it go like this? Or is it a straight line? Or do I wander off to like Alaska and then come back here? So the tricky part is what happens between them. But that is a good observation that the endpoints here, they should correspond to the endpoints here. Nice. Okay, so let's actually do this integral. We've done the hard part though, and we didn't even need to do part A to do the integral. I just wanted to do part A because drawing is fun. Yeah, and so Anouk is a good question, that if it was a linear transformation, if you plot the two endpoints, they will just be connected by a straight line. That's correct. So for a linear transformation, it would suffice to look at the endpoints. Okay, where were we? Oh yeah, part B. So this is D. That's what we just figured out. We sketched D. We want to evaluate the double integral over D of x plus y. Now this will be a change of variables thing. So what do we need to do? We need to change the bounds, we need to change the function, and we need to change the differential. The bounds we just, well, because the pre-image of G over here is this rectangle 1 to 4 cross 1 to 4, these are the U-bounds, right? We were kind of told the U-bounds in the first place. So this will be 1 to 4, 1 to 4. X plus Y, here's X, here's Y. So X is U squared over V, Y is V squared over U. And then here we're going to need the absolute value of the Jacobian, which we have not yet computed. So let's do that now. And so I don't have to keep scrolling up. I'll remind you what G is. U squared over V, V squared over U. So when I compute the Jacobian, top left corner is going to be partial of x with respect to u, which is going to be 2u over v. Let's see, partial of x with respect to v. Uh-oh, it's going to be negative u squared over, nope, yes. Negative u squared over v squared, I think. From here on out, you're going to have to check me on super basic stuff. That's what I'm going to screw up. Okay, and then y with respect to u should be negative v squared over u squared. And y with respect to v is going to be 2v over u. Maybe I did that right. And then the determinant is going to be this times this, which is 4, I think, minus this times this, which is 1. Okay. 4 minus 1 is 3. That was nice. So it looks like the Jacobian that we put here is 3. And then you could go from there. I'll be lazy again. I really don't like doing this, but we have more interesting things to talk about. So at this point, it's a straightforward iterated integral. There's nothing fancy that's happening here. You'll get some natural logs, but it's okay. It'll be just constants. And if you guys are okay with that, then here's my final answer. Yes. Good night, Lucas. Oh, but I didn't mean final answer like I'm done. I kind of want to go to 11. I think 5 hours would be cool. I don't know if I've ever done a 5-hour review session. I've hit 4 a couple times, but I'm in a record-breaking mood tonight. You can obviously leave though. Okay, so a question was, so we only take the coefficients of the derivative for the Jacobian. So we only take the coefficients of the derivative for the Jacobian. Oh, okay. Okay, so I think I get the question. Okay, so also I will say, just because I want to do math till 11, I don't think you should do math till 11. If you want my real advice, leave and go to bed, and I'll just sit here by myself and do math until 11. If you want to listen to me, feel free. But at this point, 3.5 hours in, my advice is go to bed. Okay, so to the private question, I see what you're pointing out. Yeah, you could pull up one of my YouTube videos and just put it on repeat while you sleep. That's the true secret way to learn math. So to the private question, I think she's asking like, why did I only take this times this and then this times this? So then the question is like, do I only just take the coefficients? No, this was actually a complete coincidence. It just happened that this whole thing times this, the u over v and the v over u cancel out. So it's sort of just a coincidence that this times this completely cancels out to get 1. Same thing happens here, but you do want to take the whole functions, you want to multiply everything together. Okay, cool. There's another question that I think I missed. Oh, right. So why is it 3 as opposed to 1/3? So it doesn't G map UV to XY. So would it be this? So it would be the inverse to map XY to UV. So it is genuinely 3 because anytime you do this change of variables stuff, when you start, this is really confusing, and I think it takes a lot of time to get used to, but ultimately we want to do an integral over here. This is our end goal. We change variables to get an integral over here. And when you do that, the Jacobian that you want is this direction, which in our case is G. So it's confusing, but when we go from XY to U, I almost don't even want to say this because it makes it sound more confusing than it is. When you change from XY to UV, the Jacobian that you want goes this way. So we do want the Jacobian of G, which in this case is 3. So I do want 3 here. Oh, people actually took my advice. Nice. Okay. That's probably good. Okay, so question was, the book talks about finding the Jacobian at a specific point. Would we need to do that? I mean, yeah, you could say, but I mean, there's nothing fancy there. Like I could just ask for what's the Jacobian at the point 1, 2, and you would just plug in the point 1, 2. And so like here, what if you plug in the point 1, 2 into 3? Yeah, you get 3. Yeah, you can, yeah, everyone's welcome to stay. I'm not kicking people out. Okay, so there are questions where you have to find the equation of a plane given a point in a normal vector. Could I review that? I could also deflect. I think I have a YouTube video about that. You might have to scroll back. Maybe we can do that, but I think a while ago, Trina asked about doing one of the campus wire problems. So let me do that first, and we'll do one. Let's do 1 or 2. Those are the doable ones, and then 3 and 4 are a little wonky. Yeah, we'll do both. Maybe I'll do one of them and then we'll do something else and then we can come back and do the other. Let's do the first one. So anyway, this was the first one that Noah posted on Campus Wire. And then I guess if you guys are in Cameron's class listening to this, you don't know what I'm talking about, so it doesn't matter. Okay, so what do we want to do? We've got a good old double integral to evaluate, and then D is a region bounded by a whole bunch of stuff. So what do? My first step, draw a picture. And, you know, if it hasn't been clear since I've been doing these things, but I think in these variable change problems, which, you know, the problem doesn't say, like, use a change of variables. But I think looking at these boundary curves, it's relatively clear that that's where this is headed. Because this is like a very complicated, non-simple region in any y or x sense, I can kind of already see that it's going to be a variable change problem. Anyways, what I was saying is that if it hasn't been clear yet, what I would do in these problems is I would draw, I would draw the picture in the XY world that we actually care about. And then I would also draw the corresponding picture that we'll eventually get in the UV world. I think this is a good thing to do. Noah's been doing this. I've been doing this. So if you have one of these problems, I think this is the first thing that you should do. I think it says 2x, but should it be 3x here? Or are you here, do you mean? I think both here and here are 2x. All right. So let's draw this. Let me draw, I'll draw them all in red, that's okay. Y equals x is gonna look like that. Y equals 2x would look like this. Okay, so on campus wire, one of them is 3x. Not that I don't believe you, I just want to make sure myself really quick. So actually, I think you might be thinking about the fourth question, actually. In the fourth question, it's y equals 3x, but I did just confirm, and in the first question, this is 2x, and this is 2x minus 4 as well. Makes a big difference, actually. So for the first question that he posted, this is a 2x. Okay, and then x plus 1, yeah, no worries. I mean, I've already like miswritten like 3 problems down, so very likely that I copied something down incorrectly. So if I did, please let me know. Anyway, so this other curve, x plus 1, what is this going to look like? Well, it'll be parallel to that first one I drew, so maybe it looks like that. And then 2x minus 4 is going to be parallel to this line, sort of. But it's shifted down, so it'll probably look like that. All right, there's my picture. And there's D. Now, this is an example of a problem where we're not told the change of variables, right? We're going to need to come up with it ourselves. So ultimately, we'll be seeking some kind of map G that goes from the U world to the XY world. Okay, so Elijah's got an idea, and I see where you're coming from. I think I'll actually do something a little different, yeah. I think what you're noticing is that these two equations, these first two, you can kind of pair together with a y over x, and I agree. But then what gets wonky is like here you get a y minus x, but then here it's a little different, right? Right, yeah, exactly. But no, it's a good thought. And so I think because this is a parallelogram, the things that we want to pair are maybe the parallel lines. But I do see where you were coming from there. And if this was a 1, then that would work, yeah. So what would I do? Yes, I would probably say this is the same thing as the equation y minus x equals 0. This is the same thing as the equation y minus x equals 1. And so these two equations I'll pair. And then here I could get something like, yeah. So I think Alfred suggested 2x minus y equals 0. So let's do that. And here, this would be like 2x minus y equals 4. And I'll pair those. Or like Elijah, you just said y minus 2x. You could do that too. Bounds would be a little different, but it should work out in the end. So the two relevant quantities I have are y minus x and 2x minus y. So there's my variable change. Oh, right. So then what is the corresponding region over here? Well, the green equations here tell me that u ranges from 0 to 1. And the purple equations tell me that v ranges from 0 to 4. Okay, so let me sketch that. We've got u going from 0 to 1, and v goes from 0 to 4. Okay, so Katie asked, wouldn't it be negative 4? Because I picked 2x minus y, unless I screwed up. I don't think I did though. If I picked 2x minus y, I would move the 4 over here and I would get plus 4. But alternatively, if you decided to do y minus 2x instead, then it would be negative 4, and that would be fine. And then the question was, you can always flip-flop what you call u and what you call v. That's correct. So if you said, Joe, this feels more like a v to me rather than a u, you could call y minus x v, and you could call something like 2x minus y u. And yeah, it should work out the same. Specifically because of the absolute value of the Jacobian. That's where that kind of thing becomes important. If you flip-flop, like the actual Jacobian will become negative, but when you take absolute values, it'll take care of that. So that's correct. Oh, okay. Now what do we do? Oh, right. So we ultimately need the Jacobian of G, right? But again, so this is the same kind of issue that we've talked about a couple times. This stuff right here, this describes G inverse. This is describing u and v as a function of x and y. So for us, the first thing we'd want to do is we'd want to figure out what G is. So to solve for G, solve for x and y. So let's see if I can do that. This first equation would tell me that x is y minus u, which into the second equation would give me v equals 2 times x is y minus u, minus y, which turns into 2y minus y is 1y. So I think we get that. So therefore y is like 2u plus v. Nice. And x is y minus u. So therefore, x is u plus v. Okay, and so here's roughly g. So let me write that up. So what we found is that g of uv is, the first component is u plus v, and the second component is 2u plus v. So then we can compute the Jacobian that we want. So Jacobian of g, this is going to be the determinant of partial of x with respect to u is 1, x with respect to v is 1, y with respect to u is 2, and y with respect to v is 1. So the Jacobian here is going to be 1 times 1 minus 2 times 1, which is 1 minus 2. Oh, which is negative 1. Okay, cool. Interesting. Anyway, then we're locked and loaded to do whatever we want to do. Okay, so a couple questions. In this case, could we use the fact that the Jacobian of g is 1 over the Jacobian of the inverse? In this case, yes, you can do that. Yeah. So Ileana and Luca asked the same question, which is, that's correct. You could compute the Jacobian of g inverse, which will be 1 over negative 1. It'll be negative 1. And then you could take the inverse of that, which will be negative 1. That's correct. The main reason why I'm doing this is because for Noah's class, we actually haven't talked about the inverse Jacobian yet. So I think for our class, I would maybe avoid doing that, but you could. Cool. Okay, so this double integral that we actually care about, which I think was x, yeah, is going to be oh yeah, our u bounds are 0 to 1, v bounds are 0 to 4. X is u plus v. Then I multiply by the absolute value of negative 1, dv, because that was 0 to 4, du. And so then the absolute value of negative 1 is 1. So this just turns into that integral. And then from there, it's a piece of cake. So you can probably finish it off. That's the first one, though. The main thing to take away from these problems, I think, is, well, there's a couple things. One of which is the fact that you understand why this describes G inverse. All right, let's just do it. Let's finish it off. It won't take long. Let's see, with respect to V, we'll get UV plus V squared over 2 at 4 and 0. Maybe I can squeeze it in this corner, which will get, now when I plug in 0, I'll get 0. So I get 4U plus 16 over 2 is 8. And so here we'll get an 8 in the final answer, and then 2u squared, so 2 plus 8. Whoa, so I think I think 10. That's all good. So the answer might be 10. I may have done that correctly. Who knows though? Yeah, so a private question was, okay, good night, Katie. Good luck tomorrow. So a private question was, on the test tomorrow, should we not use the inverse Jacobian thing? I would avoid it if possible, just because we haven't covered it in lecture. So one thing I'll say is, I don't care. Like me personally, Joe, I don't care if you do it and I'm grading the question. If you do it correctly and if you explain it coherently, I'm okay with that. I can't speak for Noah, and he's the man in charge. So he may feel differently, but I don't care. I'd say maybe on the safe side, if you can just find G, that might be a better thing to do. Cool. Okay. That's that one. So will the inverse just make it simpler? So everyone really wants to do this inverse thing, which is fine. But there's still something that you have to consider, which is you have to rewrite X, right? You can't get around doing that. You're going to have to rewrite X somehow. So if you want, you could use the inverse Jacobian thing to like get the Jacobian, but you're not out of the woods. You still need to figure out how to rewrite the function X. And in this case, you pretty much have to do this. There's kind of no way to get around doing this. And there you've just computed G pretty much. So sometimes there's tricky things that happen, but I wouldn't bank on the inverse Jacobian thing. And in general, it does not make things simpler. And in general, you have to be very careful because you still have to convert the function and stuff like that. So the inverse Jacobian thing is just like a cute phenomenon that sometimes happens. And when it does, it's nice and helpful. But like ultimately, especially to rewrite the function, oftentimes you still need to solve for G. So in this case, does it matter the order of dv and du? That was the next question. Nope. I mean, as long as you keep the bounds consistent, right? So the v bounds have to go from 0 to 4. U bounds have to go from 0 to 1. But since it's a rectangle, you can, by Fubini's theorem, you can integrate in any order that you want. Cool. Okay, now what? We could do the second one. Let me see if I have anything else interesting here. All right, let's just do this second one, unless anyone feels strongly about doing something else. The second one will be relatively similar, I think. Well, I don't know, actually. We'll see. Probably should have done all these myself beforehand. But I'm only human. Okay, so for the inverse Jacobian thing, it is 1 over the Jacobian. Yes. was I going to say? My true advice for now is to not worry about the inverse Jacobian stuff. It's not something that makes things significantly easier in general. Like there are some examples where it's like a nice trick that makes things much easier. But in general, you should just think about finding G's. But we'll talk about this more later. Okay, let's think about this second one. So same story as before. I've got a crazy looking region, which I'll sketch. Whoa. Oh, right, I was going to sketch the region. So I've got y equals x again, y equals 2x again. Which doesn't really look like y equals 2x. Let's see, y equals x squared. Yikes. It's going to look like that. And then 4y equals x squared. Oh. It's like y equals x squared over 4. All right, so my picture is terrible. So here's what we're going to do. Here's going to be y equals x squared. No. Sort of. Oh, thanks. Yeah, I'm truly losing it. There's y equals x squared, which doesn't even look like a function. And then y equals x squared over 4 is going to look like that. So maybe draw a better picture than I have if this comes up on a test, but I think you get the idea. And as usual, we want to figure out a change of variables to go from here to here. I'll do pretty much exactly the same thing as I did before, just that the equations are going to look a little different. And in particular, probably what we want to do is we want to pair, it seems like the x squareds are going to get paired together somehow. And then that leaves the other two. So then I'll probably pair these two. Which means I probably want to think about the region as, so the region D what would I do? Okay, so here's something. I think on Campus Wire, different people did this differently, which is totally cool. Since I see an XY here, I'm gonna make that one of the variables here. So I could write this first equation as x over y equals 1. And then this other one as x over y equals 1/2. So you could do y over x as well, but I'm tempted probably to use x over y based on the integrand. And then what about these purple equations? Again, sort of motivated by the integrand here, I can see that this is like x squared over y quantity squared. So I probably want to divide by y. And I would get something like x squared over y is going to be between 1 and 4. So then if it were me, I would let u be x over y. and I would let v be x squared over y. And I don't know, we'll see, I guess, right? If it doesn't work, back to the drawing board. So could I square, okay, that's a good question. We could. Would that make things easier is the question. Maybe. Try it. I'll do this. Try squaring it. So call v like x to the fourth over y squared or something. See what happens. The problem is the Jacobians are going to change, right? And that usually accounts for any changes that you make. So I could be wrong, but my gut feeling is that usually when you make a superficial change like that, like if you just squared everything here, it's not really going to change a whole lot. It might, but yeah, try it. Okay. Good night, Elijah. Good luck tomorrow. Anyway, so I'll try this. You can do whatever you want, though. And in my case, the region would be described in the UV world to be U goes from 1/2 to 1. And then V goes from 1 to 4, which is clearly here to here. Cool, cool. Okay, now we have the new bounds. We'll be able to rewrite the original function with no problem. What do we need to do? We need the Jacobian. And very specifically, we need the Jacobian of G. Right? So again, if you want to go against me, you can try to do the inverse thing and make it work out, but I'm just going to see if I can find G. Because again, I've repeated this a couple times now, but it's important, is that this setup right here, this describes G inverse, right? This is U and V as a function of x and y. So you give me an xy value, I'll give you a uv value. That's G inverse. We want to go the other direction. So what I want to do is solve for x and y, but it's a little tricky here because this is a non-linear system of equations. So then the question is, Joe, how do we go about solving non-linear systems of equations? You get lucky is the real answer. There's no general method here. You kind of just have to like try some shit, throw something at the wall and hope it sticks and get lucky. For example, here's what I mean by this. Well, if you guys have ideas, you can. So a private question was just checking, we integrate. So I don't know if I agree with what you wrote there. Let me write up the change of variables formula again. Never a bad thing to see. So if I want to integrate over d of f of x, y, dA, how does this change? I'll integrate over the pre-image of d, which is whatever this region is over here. And then I think this is what your question about is the thing that we integrate is f of g of uv. That's one way to write it. Or someone brought this up earlier, that alternatively, you could think about this as being f of x as a function of u and v, comma, y as a function of u and v. If that clears anything up. Okay. I know what I would do. But if anyone is still awake or paying attention, if you have ideas, you can let me know. All right, so here's an idea. And there's a lot here. It's probably correct. And yeah, my idea would be, so we could, both of those sound completely correct. We could divide u by v. We could divide v by u, in fact, to make sure that the power of x on top is bigger. But yeah, I like that idea a lot. So what I would do is I would say, note that by divine intervention, I just decide to look at v over u. Why? Because I happen to notice that the y's would cancel out. There's no methodical reasoning there. I just happened to observe that. Yeah. So if I do v divided by u, I get x squared over x, which is x. And now look at that. We have solved for x in terms of v and u. So good job, guys. Now we just need y. Well, y is, here I could just solve for y in this equation. So this tells me that y equals x over u, which, using this, is x is v over u. So this is like v over u squared. So there's x and there's y. Perfect, yeah. Okay, so now we can compute the Jacobian of G. As usual, this will be the determinant of, so partial x with respect to u, let's see, is going to be negative v over u squared. Partial of x with respect to y, and then I'll look at the questions. Let me write this stuff down really quick. Or sorry, partial of x with respect to v is going to be 1 over u. Partial of y with respect to u, negative 2v over u cubed. It's probably right. And then y with respect to v is 1 over u squared. Okay, so question, so something like this where it's not immediately obvious what we need to do for our substitution. Yeah, I mean, I think this could be fair game for the exam as written, but I do think it would be on the trickier side. I don't know. I think this could probably come up as fair game. I think, he might also just give you the substitution or give you the transformation, but this is maybe on the border of like the difficulty of coming up with the substitution yourself. Hard to say though in general. I think definitely 3 and 4 for sure. I think he'd have to give you a substitution. Well, and then even then for those questions, it's like, we saw that earlier when I embarrassed myself trying to do this problem, that even with a decent substitution, like it's not easy. So I think this is probably fair game though. Anyway, what do we get here? We'll get a negative v over u to the 4th plus 2v over u to the 4th, which I guess is like v over u to the 4th. Yeah, probably for the timed portion, it'll be quicker questions similar to so I would think about the multiple choice questions on the practice midterms as being probably indicative of what to expect for the timed portion tomorrow. And I think those multiple choice questions on the midterm, the practice midterms, were more straightforward than any of this kind of stuff that we're doing. All right, so what are we integrating? Oh, this mess. Okay, let me copy this down. Here's the integral we want. We are all set to change everything. Change the bounds. What happens? Let's see. U goes from 1/2 to 1. Maybe let me put that inside. And V goes from, what was it, 1 to 4. Yeah. So will we be given credit for work on the timed portion? Probably no. I think it'll be auto graded like the quizzes on GradeScope. Yeah. So I think it'll just be winner take all, multiple choice type questions. Yeah. All right, so there's our new bounds. How does the function change? X over Y was U. That's what I called U. So I get U to the 4th. X to the 4th over Y squared. That's like this squared, right? So that's V squared. All right, good luck, Damien. Okay, so if you did actually try it, maybe it gets difficult there. Yeah, I feel like, I don't know, I feel like it should still work. I mean, the Jacobian's going to look a lot different, but things, I don't know, things should account. I don't know though. Anyway, so the Jacobian that we want to multiply by is V over U to the 4th, du dv. Oh wow, look at that. The U to the 4ths cancel out. That's kind of nice. That's what Alfred said would happen. And we get e to the v squared times v du dv. Yeah, so good question. Or hold on. Okay, so Leah's question was a good one, which is a complaint about my U's and V's. So this guy right here is a U. I don't know which one you were referring to. They all kind of look the same to me. But that's a U. This is a V, V, U. Okay, cool. So then another question was, for some reason I'm not seeing how X over U was set to equal Y on the right side. So where did this come from? That came from, do I even know? Yes, good night, Richard. Good luck tomorrow. That came from here. So the original variable substitution we had was U equals X over Y. So I think all I did was I solved for Y there. I get X over U. If that's what you were asking about, I think that's where that came from. Good night, Myra. Good luck tomorrow. All right, let me finish this guy off because we're close. Integrating with respect to U, I'm just going to pick up a factor of 1/2. I'll do that in my head, and that'll leave us with 1 to 4. Okay, so Ileana's got a good question. Let me come back to that really quick. So let's see, here we get another factor of 1/2 at 4 and 1. So again, who knows if I actually did this correctly. Something like that. Oh, hey. Hey, Marley, I didn't know you were here. Well, good to hear from you again. Good luck tomorrow. Anyway, that's probably that one. Okay, so Ileana's question is, whoops. If the bounds are like negative to positive, how do we break up the integral to take into account with the absolute value of the Jacobian? So I'm going to give you maybe a non-satisfying answer, but if things are happening correctly, so what do I mean by that? I know you've taken 33A, Ileana, so actually I'll just give you the real answer, which isn't that hard. I was gonna sugarcoat it a little bit, but what do we know about any change of variables map? This may have been kind of skimmed over in lecture because, you know, it just always works out for us, but one of the really important features of this change of variables map is that it's invertible. G needs to be invertible for any change of variables to make sense. Or, you know, maybe we don't know what well, yeah, we know what invertible means. It needs to be 1-to-1 at least. Now, the fact that G needs to be invertible means that the determinant of its linearization is always going to be non-zero. I don't know if that makes sense, but, you know, we know that invertible things roughly correspond to a determinant not being 0. Yeah. So when you make a change of variables, technically you're only allowed to do that when the G map has a determinant which is never 0, which means it will always either be positive or always either be negative, in which case you shouldn't ever have a scenario where you'd have to break things up into multiple integrals. That's a good question though. And that's an indication that if that kind of thing happens, like if you do something and then you realize like, oh, I'm gonna need to split this up because of the absolute value, that means you didn't do something correctly. So that could be kind of a red flag to indicate that maybe I should do something else. But yeah, that's a good question. Okay. Any other questions about that one? Oh, right. So go back to the question that's similar to question 3 from the practice midterm. Oh, the one that I did, yeah. Maybe let me ask this. You know, I know the practice midterms have been out for a while, but were there any questions from the actual practice midterms that you guys wanted to talk about? Now that I've done a lot of what I wanted to do. So I'll pull up the notes here. Alfred, I don't know which part you wanted to see, but there's some of it. Yeah. Like I said, after this, I'll post these notes on my website as well. So. Yes. Oh. How many people do we still have? Still over 40. Damn. You guys go hard. I'm impressed. example 4 from Campus Wire, you mean the extra one that Noah wrote? We could try. Let's try. Maybe we'll get, let's see what happens. Okay. That sounds like a good idea. That's the kind of substitution that I think we want to make, which is similar to the nonsense that I was talking about up here, where I was like, oh, you want to flatten one direction or something like that. So let's try that and see what happens. So number 4 from Campus Wire, like I said, this is another tricky one. We're given the same double integral again. Yes, you're welcome, guys. Good night and good luck. Double integral of x over d. This time d is all these regions look really similar. Y equals x, y equals 3x this time. X plus 2 and 2x minus 4. Okay. So we do the same same song and dance as always. And then I'll use your variable substitution. We'll give that a shot because that sounds like a good idea to me. Let me sketch this picture really quick. We've got y equals x, which looks like that. Y equals 3x is going to maybe look like that. X plus 2 is going to be parallel to this first line. So something like that. All right, and then the reason why these things get tricky is because y equals 2x minus 4 is going to look, so it'll be between, the slope will be between this line and this line, so it'll look like that, and it'll be shifted down. So I don't know, maybe it looks something like that. Okay, so here's our goofy region that we care about. Now, I think we should think again about this kind of pairing type thing. And so the suggested substitution, which was, let's call u equals y minus x, that comes from pairing, whoops. It's not what I wanted to do. Comes from pairing this equation and this equation, right? So the region we care about in the xy plane, which is, I guess, D, I'll label it. So I'll say D is described by those purple equations I could write as y minus x goes from 0 to 2. And then, you know, the other equations are a little wonky looking. So instead of trying to do something fancy with them, let's just say, if it were me, I would say y goes from 2x minus 4 to 3x. So you suggested v equals x. I think that should work because I'm lazy. To me, this inequality feels a little bit more natural than writing an inequality in terms of x. Like you could solve for x here and get an inequality that way. I think probably what I'll do is I'll leave it like this, and I'll think about v as being my variable. Sorry, y as being my variable. So try your own thing, and it should work out the same also. The algebra will be a little different initially, but for the sake of doing something different, let me call v y. But like I said, I think they should more or less be the same. So what happens? Well, this first inequality turns into 0, u2. Come on. And then the silly part is going to be figuring out this second inequality. Well, in the middle, I've got v. What we'll have to do is we'll have to figure out how to rewrite these in terms of u and v. That's actually not so bad, just because here, if I solve for x is y minus u, but y is v, right? So x is v minus u. So I didn't give myself much room here. But on the left-hand side, I would get 2 times x minus 4 is less than v is less than 3 times x is v minus u. And then let's simplify this a little bit. Let's see, so I get 2v minus 2u minus 4 is less than v is less than 3v minus 3u. What am I doing right now? I want a bound for v, so I need to solve each of these individually for v. So this boundary has equation like this, which if I solve for v would be v equals 2u plus 4. And then yeah, so I think you've got it. I'll catch up to you here. This would be v equals 3v minus 3u, which says 2v equals right 3u. So therefore v equals 3/2 u. So that was fun. All of this turns into our u inequality is 0 to 2. And the v inequality, the lower bound is going to be 2u plus 4. And the upper bound is going to be 3/2 u. Okay, so that was a little haphazard, a lot of algebra, but what have we done? We've now found the new bounds, right? We've figured out how to redescribe our region that we care about. Whoops. Which was described by these inequalities, and we've successfully, took me a while, but turned them into u and v inequalities. So we've got the new bounds. Next, we'll need to change the function, and we'll need to change the differentials. And to do that, like before, I think we'll probably need to figure out the function g. But actually, this is pretty straightforward, right? Here, we've already solved for x in terms of v and u, and then we've already solved for y in terms of v and u too, right? Y is v. So this tells me that g of u and v is x is v minus u and y is v. And that's what we can use to compute the Jacobian. Thank you, Anais. Good luck tomorrow. Yeah, I think even 4.5 is a record. I'm going to go for 5 hours. I'll go till 11 and then I'll stop there. I should probably go to bed after that. You should too. So, all right, so let's do the Jacobian. This will be determinant of partial of x with respect to u is -1. Partial of x with respect to v is 1. Y with respect to u is 0. Y with respect to v, maybe by the end of the quarter, we'll go for 6. That could be like a finals review session, 6 hours. That'd be kind of fun. I'd really need some pre-workout for that. Y with respect to v is 1. Also, probably by that point, I would just be saying insane things and it wouldn't even be helpful to be listening to me. It might not even be helpful listening to me at this point, 4.5 hours in. I don't know if I trust anything that I'm saying right now. Anyway, the determinant here is going to be -1. Okay, so I think we're ready now. This one wasn't so bad, actually. 3 is disgusting, but this one's okay. Anyway, so this new integral that we want, the new bounds, here the order really does matter, right? Yeah, I guess could keep going until the iPad dies. My charger's all the way across the room, so I don't know if I'm willing to put in the work to go get it. What was I saying? Oh, the order in this case does really matter, right? Because this is not a rectangle. We need to do v first because of the variable bounds here. So in particular, I'll do dv. I'll go from, I think that says 2u plus 4. I can't even read my own handwriting. To 3/2 u, and then u on the outside will go from 0 to 2. X, the function that we're integrating, is v minus u. The absolute value of the Jacobian is going to be absolute value of -1, which I think is 1, dv du. And then it's not so hard from there. So you could finish it off. Yeah, it wasn't so bad. Hardest part here is definitely coming up with a helpful variable substitution. I think the weird bounds make it a little goofy. Yes, I will scroll up. You can tell me when. So is that v is bigger than 3/2 u rather than less? Yeah, I screwed that up. Good catch. Sorry about that. I knew something was wrong. So these should be in the other order, right? 3/2 u is smaller. Can we try 3? Yeah, maybe now that I'm half delirious, we can make it work. Let me fix this really quick and then I'll go back to 3. Oh, 3/2 u, and then 2u plus 4. Okay. We'll see if I can redeem myself. keep my picture up. That looks okay. Let me get rid of all this nonsense. Okay. So we're in this together now. Yeah, so I like x minus y, or something like y. I'm going to stick to y minus x. So I'm going to stick to straightening out these guys. So D is described by on the one hand, if I pair these two equations, I would get y minus x goes from 0 to 1. I don't feel like x plus y will work. I can't remember what we tried last time, but I guess what I'm tempted to do is maybe x, let v be x. So for example, if I pair these two, I could rewrite this as x is between 1 over y and 2 over y. So yeah, fair, I think that's a good choice, and I think that's what we tried last time. And I think it would ultimately work. I mostly just got lazy. Last time I did v equals y, so to get rid of bad karma, let's do something different. But yeah, I mean, I think v equals y should probably work too. I'll switch it up this time. What's the thing about insanity, like doing the same thing over and over again, expecting different results? Anyway, I mean, it won't really be much different. I'll try to be more careful about this. Let's try this. I'm gonna let u be y minus x and v be x. So this first inequality is great, no problem there. And then what happens with this second mess? So I'm gonna be a little more organized about this. I'll do this in green. I'll call this star, and then this might take some work. So I'll do this in a little separate blurb. So I want to translate this second inequality into u and v. While v is x, right? So the middle thing is x. And we need to figure out what to do with y. So note that using this first equation here, y is x plus u. Well, x is just v, so y is u plus v. Oh, and I don't know why I wrote x in the middle. I want to write x as v. So 1 over y will be 1 over u plus v. And this will be 2 over u plus v. So this turns into 1 between v times u plus v between 2. All right. I can't think of anything else to do, so I'll just do the same thing and we'll be careful and we'll persist. So this is like v squared plus u times v. And then I want to complete this square, so I will add u over 2 quantity squared, so u squared over 4. Then we need to subtract u squared over 4. I think that's right. We'll get v plus u over 2 quantity squared minus u squared over 4 is less than 2, which add the u squared over 4 to both sides. I get that. Take a square root. Now let me just run a sanity check. Is v plus u over 2 positive? V is x, and x is always positive. So v plus u over 2, yeah, it's going to be positive. All right, so we want the positive square root. Okay. So, yeah, I mean, this is what we got last time, and it's ugly, but that's okay. Now that we've done everything that I wanted to do, I'd feel less bad about spending time on this. How many of you are actually still watching me do this? 26. The few and the proud, right? Okay, and so here's, whoops, forgot this side. There's our inequality for v. And it looks ridiculous, and it is, but I don't think there's any getting around that. Can't do this on a chalkboard. Scroll down to number 4 from the problem set. Let me finish this one, and then I can scroll down. And like I said, I'll post these afterwards if you want to look at the solution. While I'm on a roll, though, let me keep going here. All right, so here's our description of the bounds. Looks vile, but that's okay. What else do we need? We need depending on how long this problem takes, we might go to like 11:30. Okay, so we've got the bounds. We need the Jacobian. Changing the function is easy because it'll just be x, which is, oh no, the function's disgusting. Damn it. That's okay, but we can change it. So we need the Jacobian. But what if we found, yeah, we'll need the charger soon. G of u v, x is v, right? And then what is y? Y is right here. We already solved that. That's u plus v. Uh-oh. Sorry about that. Okay, so there's our function. If that part's fine so far. Damn it. So Jacobian's easy enough to compute. X with respect to u is 0, x with respect to v is 1, and then 1, 1. Looks like we'll get negative 1 here. So this integral of x squared y squared dA, by the change of variables nonsense. So we're going to have to do v first. The outside bounds in terms of u are 0 to 1. Inside bounds are these disgusting things right here. So let me call, I'll just write it down. Negative u over 2 plus root 1 plus u squared over 4. Negative u over 2 plus root 2 plus u squared over 4. And then, okay, x squared is v squared. Y squared, what was y? U plus v. Okay, times the absolute value of negative 1 is 1. And then we got to do dv du. Okay. Shit. All right. Take a deep breath, and here we go. I can't think of any other tricks at this point to do. So I'm way too lazy to write those things out now. This is going to be v squared times u squared plus 2uv plus v squared. Which is going to be v squared u squared. What the hell? There's no way. Did Noah ever actually do this one? Like, did he give a final answer on Campus Wire? This is ridiculous. Yeah, nice. Good point. I mean, I guess we could just plug this into Wolfram at this point. Maybe that's what he wants me to do. The problem here is that when you integrate with respect to v,
You said that on the actual Campus Wire post, he said I haven't worked out any of these myself.
right? I didn't know if he ever did in any of the comments or anything. I'm suspecting at this point, You just plug into Wolfram. I mean, I know that's a cop-out. We could think about integrating it, but the problem, you know, we could think about, so Farah's asking about like polar coordinates or something. I don't think so. Because the region's not really circular. It may seem that way based on like these square root expressions or something. But the fact that it's like 1 plus u squared and 2 plus u squared kind of throws everything out of whack. So I don't think polar would work here. I think if there's anything you can do, it's going to be brute forcing this antiderivative. Over 2. Yeah, and the problem is like maybe this term is okay. But like when you plug this mess, yeah, like when you plug this mess into like these odd powers, it's not gonna play nicely. Especially this like v to the 5th term, you don't have any factors of u here to help you out. So unless I'm just missing something, I don't think I could do this by hand. Yeah, I think at this point it's just like a plug into Wolfram thing. No reasonable person would try to do this by hand. This seems hard. Plug it into, yeah, pretty good timing actually. Plug into online calculator or skip. Or, you know, maybe there's something I'm missing and you can do it much more easily. And then I get a 5 out of 10 on this question and I can't even do math 32B and I'm the TA for it. That's a possibility as well. But I think no matter what you do, it's complicated.
Oh, he has the bound. Someone posted a graph, and then Noah said what the bounds were from the graph.
So Noah got the bounds, he said?
So, it's Q2, maybe. Wrong. It's like a smorgasbord of. I don't think you ever solved this question, to be complete.
I hate admitting defeat, but I don't think I can do this one by hand. I'll just lay that out there. If it's
try something like v equals y, but like.
Right. I mean, I get that, but that's what we've tried, and yeah, like v equals y or v equals x is pretty much the same thing.
Also, if you follow the really messy original method from this user, whatever.
Yeah.
So he gives you.
Does that work out?
He says it ends up being vertically simple.
That's fine. I mean, this region that we got is horizontally simple.
Yeah, I don't know. I'm just reading everything.
Yeah, no, it's okay. I'll look through the comments. My hunch is that no matter what you do, this is kind of a mess. And I'll say that knowing that I could be wrong. And not liking to admit to be wrong, but I don't think I can do this. So
I think Noah owes us a fully written out answer.
Yeah, I mean, like if we were grading this question, I'm probably not even going to look beyond like here. So like if you can get here, I think you're fine. Yeah, so I mean, this is a shattered record. I think my previous record was like 4 hours for a review session last quarter at some point. So it's pretty solid.
32B is a lot harder than
Yeah.
32.
Also, it's a lot different leading a review session from my room than having to stand up and walk back and forth for 4 hours. That takes a toll.
No, that's why I said anyone know Conley, because Conley's known
Yeah,
for
right. It's tough. It's exhausting. Okay, I'm gonna call it there. Let me stop recording. But good luck tomorrow. Don't worry about it too much. Spend an hour or two at most, turn it in, and move on.